Welcome back, guys. This is chapter number 5 and here we are at section 5.1. okay, what do we have to do here? This is question number 2 and we have to write the output expression for each of the circuits given in figure 5.54. okay, so this is figure 5.54 and here we have two parts, part A and part B. So let us start part A here. okay, so in part A we have three inputs, A, B, C. okay, so A, B, C are given to different gates here and we have to find out the output of each gate, and at the end we have to find the value for the output X. okay, so what are these? So let me first use different colors for each of the gate here. So for this gate I am going to use this yellow color. For the second gate here, this AND gate, I am going to use this color, and for the other gate I am going to use this color. okay, so these are different gates, and after it I will get the output, and for that output I am going to use what? I am going to use, let me use this white color for it. okay, so here I will use this white color. So let us first start it. So here the output of the input A, B, C, the first input A is given to this NOT gate first, and the output I am getting from it is this A complement. okay, because it is now inverting the input which is given to it. So now the output of it is this one. okay, this is the yellow color. Similarly, the B is given to this AND gate. okay, this is the AND gate. Here this B is given with this A complement, and what are we getting out of it? So we can see that what is the color which we are using for it? This is this light green. okay, so let me use it for this light green. So here this is the output, and here what are we getting? Here we are getting this A complement with this B. So using this A complement and this B which is given to it, so this is now B here. okay, and this is the output of this gate. Similarly, we can see here that this A and this C are given to this gate. We can see here that this is A, this is C, and the output of this gate is with represented with this blue color. So the output of it is what? This is the AND gate, so therefore this is A dot C. okay, so the output of it is A dot C, and the both of these inputs are given to what? These are given to, let me see it, this is the output of this AND gate. Similarly, the output of this AND gate, these twos, and similarly the output of this NOT gate which is represented by this yellow color. okay, these are given to this what? This OR gate. okay, so the output of it will be X. So let me write this X. So X is equal to what? The first input which is given to it is this A complement. So let it write it with this A complement, and then it is what? This is OR. okay, and as this is the output of this, so let me write it A dot D. okay, and similarly it is ANDed with this. This is the second input, and the third input with this is this one, A dot C. okay, so what is this? This is the output X, and that is the required output which we wanted. So all of this is now white colored because this is now the output of it. okay, so that is the answer of my question, which is here. okay, so that is the answer of part A. Similarly, in order to solve part B here, what do we have to do? Again, we are given some inputs. So now the inputs we have are 4, A, B, C, and D. okay, and here again we have different gates here, and as we have many inputs here, so instead of following the procedure or colors which we have previously used, let's us use some other procedure here, and that is to use this yellow color for these gates. okay, these are the NOT gates, and for these gates I am going to use what? I'm going to use this color, and this is again the NOT gate, and this is the OR gate, and for the OR gate I am going to use here this red color. Okay, so these are different gates. So initially this A is given to this inverter, and here we will get this A complement here. Okay, this is the A complement, and also this A complement is also given to this gate as well, that is the A complement. Similarly, this D is also given here, and it is now applied, and this is now what? This is the D complement, and D complement is given to it. Okay, so at the output of this gate, and this gate, what are the signals which we have? So here we can see that two inputs are applied here. First is the A complement, the second one is B, and at this output what are we getting here is that this is the AND gate. So A complement dot B is the output here. Similarly, to this gate, this is the second gate, and here what are we getting, or what have we applied here? We can see that here we have three inputs. The first input is this A complement, okay, this one. The second is C, while the third one is this D. So therefore the output of it is what? The output of this gate is A complement dot C dot D. Okay, so these are the three inputs which are applied here. And similarly, to this third gate we have this input, and what is this? This is D. Okay, similarly here we have this B, and here D complement as well. So the outputs here are what? These are, here we have this B, okay, which is applied here. Similarly, we have this D here as well. Okay, we have this D here, and D complement here as well. Okay, so these are the three inputs which are applied. So these three inputs are now given to this gate, which is basically the OR gate. So after ORing it, what would we get? So let me write it here. So I will get here A complement dot B plus, because three inputs are added now. So here I will get A complement dot C dot D plus this B dot D dot D complement. Okay, so this is what? This is the output here, and in order to find the X, what would we have? All of them will be complemented. Okay, so X will be what? X will be the complement of A complement dot B plus A complement CD plus B D D complement. Okay, and that would be the whole complemented one. Okay, here we can very easily see that this term is now 0. Why is it 0? Because D dot D complement, this is always equal to 0. Okay, so removing it from here, what I will get? I will get here A complement dot B plus A complement CD. So this is basically the output of this gate. We can also simplify it by using the DeMorgan's law. Okay, but I am leaving this as it is here. So that's it for today. Welcome back, guys. This is question number 3 of chapter number 5, and here we are in section 5.1. So we have to write the output expressions, okay, for each of the circuit as it appears in figure 5.55. So this is figure 5.55, and here we have different parts. Okay, so let me solve them here as well as we have done previously. Okay, so the first gate here we have is this gate, and the second one in part A is this gate. So we have here these two AND gates. So let me give different colors to them. So the first to the first gate I am giving this yellow color, and to the second gate I am applying this green color. So the output of it will be X. So after the first gate, what will be the output? So let me represent these outputs with the same color with which the gate has been represented. So A and B has been applied here. So the output of it we will get will be here, and it would be AB. Okay, so now this AB will be applied, and this B will also be applied here to this AND gate, and the output of it will be what this will be. The output of it will be what AB dot B. Okay, because AB and this B are now ANDed together, and we have got this output, which is basically the output, and that is basically the answer of part A here. Okay, similarly, now for part B here, for part B, let me use the same colors. So this is a yellow color here, and for the second gate I am applying this green color. Okay, so for the first gate, the output of it will be AB, because this is the AND gate. Okay, and then this input is given to this OR gate along with this input, which is the B. So the output of it will be what? That would be the AB plus this B, and that is the answer of this question. Okay, so that is the answer of part B here. Okay, that is AB plus B. Similarly here for part C, let me use this yellow color for this NOT gate, and this color, this green color for this OR gate. Okay, so here we can see that the output of this NOT gate would be A complement, which is applied here to this gate, which is basically the OR gate, and after it what will happen, this A complement is now OR with this B. So here what I will get or A complement plus B, and that is basically the answer of part C. Okay, so we have solved these three parts. Now moving towards the part D here, let me use the colors. So let me first use this yellow color for the first gate, which is the OR gate. Similarly, this color for this second AND gate, and the third gate, which is this OR gate, and giving it this blue color. So now the output of them would be the first two inputs which are applied to this gate are AB. So at the output of it I will get A plus B, because this is the OR gate, and similarly to this gate two inputs, the same inputs are applied, and here we will get AB. Okay, so when these two will be applied, so we can see very clearly that this yellow and this green inputs are applied to this OR gate, and at the output what would we get? We will get here what? A plus B, okay, plus AB. So that is what, that is the output or X of this question, and we have got the answer of it. Okay, similarly for part C here, this is part C, and again using the colors which we have previously used. So this is the yellow color, okay, this is green colored gate, and the third gate here is, let me use this blue color, the same color here. So what would be the outputs here? So here we can see that A and B will be applied here, and as this is the NAND gate, because of the bubble which can be seen here, so the output of it would be what? That would be AB whole complement. Okay, so this is applied here. So after it this B is applied, and due to this B, the output of the second gate would be what? That would be AB whole complement with this B, okay, which is applied here, and after it this C is applied here. We can see that this is another NAND gate, and here when these two are applied here, the output of it would be what? That would be the AB whole complement dot B, okay, and with it the multiplied term is what, that is C, and at the end all of these are complemented together, and that is the solution of part E here. And as we can see here that we can also simplify it by using the DeMorgan's law as well, but I am not solving it, or I am not doing it because I just have to find the output of these gates. Okay, similarly here, let me see the outputs are here. So let me represent this NOT gate or inverter with this yellow color. Okay, similarly the second AND gate with this one, this gate with this bluish one, and the output gate with this white color. Okay, so this is the AND gate. Okay, so the inputs which are applied here, so here the first is B complement which is applied here, and to this first gate, okay, this OR gate, two inputs A, B are applied, so I will get A plus B which are applied here to this AND gate. Okay, similarly to this gate we have two inputs and these inputs are applied, and at the output we will get B complement plus C which are applied here to this gate. Okay, so now after it, what would happen at this gate, at this, as this is the AND gate, both of these inputs will be multiplied together and the output of it will be what, that would be A plus B multiplied it with the B complement plus C. Okay, so that is what, that is the answer of this part, which is part F here. Okay, so that's it for today, in which we have seen the expression or output expressions for all the gates which are given to us, and we can implement them in the later topics. So that's it for today, and I hope you have understood all the steps which are covered in this question, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself. Welcome back, guys. So this is question number 4, and here what we have to do, we are asked to write the output expression for each of the circuit as it appears in figure 5.56. okay, so this is the figure 5.56. we can see that it consists of many parts which are A, B, C, D, E and F. okay, but today we are going to solve just part A and B here. Okay, and then change each circuit to an equivalent and or configuration. How to change the configurations which are already given to their and or configuration, we will see it later on. So let us have these part A. So in part A we have 4 inputs which are A, B, C and D. okay, so these are basically the 4 inputs which we have. So here the inputs which are given to each of the part, let me give them certain colors. So to the first part or the first gate is given this green color. okay, to the second one, let me give this yellow color to it. okay, and to the third one, let me give some other color. So let me give it this light blue. okay, so the output here we will have it in the form of this light blue. okay, so let me write the outputs. So the outputs here are, okay, this is AB. so AB is when given or applied to this circuit. okay, we can see that these two are inputs are applied here, and out at the output of it we will get this, and the output of it we will get A plus B. okay, similarly for the second circuit, what will be the output? The output here will be, let me use this yellow color which I used or to denote it. So these are the two inputs which are CD. CD are applied here, and at the output we will get C plus D. okay, so these are basically the two inputs which are applied to this AND gate now. So at the input of these AND gates we have two inputs which are here, this is A plus B and this is C plus D. so the functionality of this AND gate is that these two will be multiplied together and we will get what, let me see that. So at the output of it we will get here A plus B multiplied by C plus D. Okay, so that is the answer of this question which we have seen. So this is basically the answer of my question, which is part A. Okay, so this is the output of it. Similarly, after it we have this part B here, and let me use it here. So we have 4 inputs again, one A, B, C and D. Okay, so these are the 4 inputs. So in order to denote different outputs of the gates, let me write or give each gate some color. So let me again give this gate this light blue. Okay, this is the first AND gate. The second gate we have here is, let me give it this yellow color. Okay, this is the yellow color. The third gate here is, let me give it this light green. Okay, and the output of it, which is here this OR gate, let me give it which color? So let me give it this orange color. Okay, so the orange color, this is the output. So when AB is applied here, let me write it. When AB is applied here, we can see that this is which gate is this? This is the NAND gate. So at the output of it, we will get AB whole complement. Okay, so that is the output of this NAND gate. Similarly, this is now applied here, and with it this signal, this is C, this is also applied here, and at the output of it, this is another AND gate, NAND gate, sorry, because of this bubble here. So at the output of it, what I will get? So let me draw it again here, and this is with this light green. So AB whole complement multiplied by C and the whole complement. Okay, so at the output of it, we will get this signal. And here we can see that here we have 2 inputs. One is, let me use the yellow color. So one is this D, the other one is this C. So at the output of it, I will get CD whole complement. Okay, so this signal is applied here, this green is also applied here, and the output of it, as I am denoting it with this orange color, so at the output of it, what I will get? I will get AB complement C and whole complement. Okay, and plus with it is CD whole complement. Okay, so what is this? That is the solution of this question which I have solved here. Okay, so the second question is how to convert them to each AND OR configuration. How to do it? So we can do it by using the DeMorgan's law here. Okay, so by applying DeMorgan's law here, we can very easily convert it to the feasible form, which will be in the form of AND OR configuration. Okay, so that is the solution we have seen for part A and part B, and I hope you have understood all the underlying steps which had to carry on in order to fulfill the statement which has been given in the form of this statement. So the same procedure will also be followed for part C, D, part E, F as well. So I think it's enough for today. If you guys got any question, you can ask me in the comment box. So I hope it's enough for today. So thank you so much, and I will see you soon. Hello guys, I hope all of you will be fine. So this is question 5, in which we have to develop the truth table for each of the circuit in figure 5.55. Okay, so previously we have developed the Boolean expressions for all the circuits which are given in figure 5.55. Okay, so here we have to draw the circuits or develop the truth table for them. Initially we will consider all the circuits in which the inputs are 2, which are A and B. So let me use them here. So these are basically the expressions which we had here. So these are A, B, C and D. Okay, so let me first simplify them. The simplified version of it, as we can very easily see that according to the Boolean's law, A, B is here. So B dot B is always B. Okay, so let me write this expression as what? Let me write it like this can be AB, okay, because B dot B is following this rule. Okay, this is the part A simplified version. For part B, we can very easily see that by taking this B common from here, what I can get here B A plus 1, okay, and according to the Boolean algebra, we know that A plus 1 is always 1 because anything plus 1 is always 1. So therefore what I will get here, I will get here the simplified version of it, and that is here B multiplied by 1, which will ultimately give me B. Okay, similarly the others will remain the same, as there is nothing to find here, but this will remain the same, while for it I can also take this B common from here. So here it will be A plus B 1 plus A. Okay, so what I will get here, from here I will get A plus here A1 plus A is 1, so here I will get B. Okay, so the output of it will be A plus B. So this is the simplified version of part D. Okay, because from here we have taken this B common. Okay, when this B is taken common from here, it is now this one, and from it the simplified version is A plus B. Okay, so now let me use the table which is for the A and B. So let me take different combinations of A, B. So 0, 0 is the first combination, 0, 1 is the second combination, 1, 0 is the third, and 1, 1 is the fourth combination. So it has different combinations. For part A, let me write it with this color. So let me use the orange color for it. So here we have this AB, this is for part A. Okay, so for part A we have AB. So let me write these for it. So AB is, this is 0, this is 0, this is 0, this is 1. Okay, you can see that 0 multiplied by 0 is 0, this is 0, this is 0, and this is 0. So this is the truth table for part A. Okay, similarly for part B, let me use some other color. So let me use this light green for it. So here we have this B. Okay, for this is part B here, this is A. So for B, what will be the output? It will be the same as it is here for B. So I will get here 0, 1, 0, 1. Okay, so that is the output which it has. So that is for part B here. Okay, so let me separate out by using these. Okay, for B here, let me use this one. Okay, this was for part A, and for these two, let me, I have used this one. So these are basically the values, while the outputs are here. Okay, for part C here, let me use another color. So let me use this bright blue for it. So for part C we have what, this is A complement plus B. So we have A complement plus B, and this is for part C, and let me draw it like this. Okay, and this one is here. So what it will be, so let me write it. So 0 complement here, it will be what, it will be 1. 1 plus 0 is 1, so it will be 1. Okay, similarly here 0 complement is 0, 0 complement is 1, 1 plus 1 is again 1, so let me write it here as 1. Here 0 complement 1 complement is what, here the 1 complement is 0, 0 plus 0 is 0. Okay, and here it is, we can see that this is the value of A complement is 0, 0 plus 1 is 1. Okay, so that is the output for part C. Okay, we have seen that we can find out very easily. For the last part here, which is part D, let me choose another color. So the color I'm going to choose here is this one. Let me use this one, and that is here A plus B. Okay, so that is A plus B, and this is part D. Okay, so let me separate it out. Okay, so this is a plus b, and now let me write it. So a plus 0 is 0, 0 plus 1 is 1, 1 1. This is a simple OR gate, and the output we have got is here, this one. Okay, so that is the solution of part D here, and here we have solved all the combinations for which the input was composed of two elements, which were A and B. In our next part, we will solve all other parts of our question here. So I think it's enough for today, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. This is question number 5, and today we are going to solve the two remaining parts of this question. Okay, so previously we have seen that how to find the truth table for the circuit which is given in figure 5.55, and this was basically a question which is solved here, and we have solved previously part A, B, C, D, but today we are going to talk about part E and part F. Okay, and the expression for them are here and here as well. Okay, so the question we are given here is this one, and here we can see that we have 3 variables, and what are those variable inputs are A, B and C. So let me write them here. So these are here, so let me write them here: A, B, C. Okay, so these are what? These are basically the combinations of the input. Okay, so let me write them and use this white color for it. So 0 0 0, 0 0 1, 0 1 0, and okay, so 0 1 0 and then 0 1 1. Okay, these are the first 4 combinations. Then now 1 0 0, 1 0 1, 1 1 0, and the last one is 1 1 1. Okay, so on the basis of it we have to see that what are the values of these inputs. So let me write it here, the parts of my input. So the first part of it is AB complement. Okay, so after it I have to write BC. Okay, and then AB complement dot BC. Okay, and then what? Then I have to write AB complement dot BC and the whole complement of it. Okay, so in this manner we have split our question or part E, okay, into some parts, and we will see that it will be easier for us to tackle down this question now. Okay, so now let me write different combinations of it. So this is here, 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 and here as well. Okay, so let me write them here. So AB here is 0 0 and 0 0, and this is 1. Again this is 1, this is 1, because 0 1 is what? That is 0, so complement of it is 1. Similarly here 1 1 1, here 1 1 is 1, so complement of it 0, and here is 0. Okay, similarly BC here, if any one of them is 0, so the output of it will be 0. So let me write it here: 0 0 0. Now we can see that both of them are 1, so it will be 1. Similarly 0 0 0, and here 1. Okay, so after it we have to multiply these two together to get this one. Okay, so how to find it out? Let me multiply them. So if any one of them is 0, so it will be 0, so it is 0 0 0 1 0 0 0 and 0 as well. Okay, so this is the output, and in order to find the complement of it, what I have to do? I have to find the values of this expression, which is the whole complement, and make zeros 1 and 1 0. So here it will be 1 1 1 0 1 1 1 and 1. Okay, so that is the procedure of finding the outputs. And what is this? This is basically the table. Okay, this one is basically the answer of part E, which I had to find out here. Okay, so that is the part E here, and we have found their output. Okay, similarly, now let me remove them and find the other expression which is here. Okay, so let me remove them. Okay, so now using the same combinations which we have here, because again we have three inputs A, B, C. So here first of all let me find A plus B, then B complement plus C, and here A plus B multiply it with B complement plus C. Okay, so that would be the output. So let me write them. So A plus B, if any one of A or B is 1, the output will be 1. So it is 0, 0, 1 here because now B is 1. Okay, similarly here 1 because this is 1. Similarly the other ones because now this is 1. Sorry for it. Here this one is also 1 because now two of them are 1, so output will be 1 as well, and here 1 as well. Okay, so similarly here for this part, B complement plus C is what? So B complement is 1 here, plus C is, so this is 1. Similarly here 1. Okay, so B complement here is 0, and 0 plus 0 is 0. Okay, here 1. Okay, here this B is 0, so B complement is 1, so 1 plus 0 is 1. Here it will also be 1. Okay, it will be 0 because now Z1 is complemented and it will be 0 now, so 0 plus 0 is 0, and here 1. Okay, so here we have got this expression. Okay, so now in order to find the final expression which is here, I have to combine this one and this one, and I have to multiply them together, and in multiplication I can very easily see that if any one of these twos, okay, if any one of these twos is 0, the output will be 0. So here it is 0, it is 0, it is 0. Okay, this is 1 because both of them are 1s, and this is the only condition for the AND gate to get the output equal to true or 1. So that is 1, 1, 1. Okay, this is 0 and this is 1. Okay, so what is this? This is basically the output expression. Okay, this is the output expression for the part F here, and we have found out that we can very easily find out the expression or the truth table for the expression after finding the Boolean expression for the circuit and then solving it like this one. Okay, so that's it for today, in which we have seen the remaining parts of our question. So I will see you with some more question in our upcoming video. Thank you so much. Welcome back, guys. So this is section 5.2, and here we are starting the implementation of combinational logic. So we have here question number 8, and here the statement is develop an AND or invert logic circuit. Okay, so AND or invert logic circuit for a power drive. Okay, so we have a power drive which switches on. So the power drive will switch on when the guard is in place. So the input signal to it is given from a guard and switches off. So the second state is switch off when the motor is too hot. Okay, so when the motor is too hot, the input is 0. Okay, so let me solve it first, and in solving it we should see that what are the steps. Okay, so the step 1 here, let me write here step number 1 of solving this kind of questions. So first of all we have to write it in our own language, that we have to see what are the inputs. Okay, so the input signals to the block are what? Okay, so if this is a block, okay, then we have two inputs here. Okay, what are those inputs? The first input is of guard, okay, and the second one is motor is cool or not. Okay, so guard and MC, and it has just one output, and that is of switch. Okay, so on the basis of the guard and motor cool, we have to switch on or off. Okay, either it will be on or off, and this will be a circuit which we have to design here. So on the basis of it, what I have to do, I have to devise the step number 2. Okay, and in step number 2 what I have to do, I have to draw the truth table. Okay, draw a truth table. Okay, so in truth table what we have here, we will have inputs and here we will have the output. Okay, so on the basis of it, let me see that what inputs do we have. So the inputs we have here are guard and what, MC, and the output here is the switch. Okay, so these are basically our inputs and outputs, and the combinations of the inputs are 0 0 0 1 1 0 and the last one is 1 1. Okay, so let me write the combinations on the basis of it. So we can see that from this statement we can see that the switch will be on. Okay, it will be at logic 1 when the guard is in place. So when the guard is in place, it means it is 1. So in these two conditions the guard is in place, so I have to write 1 here and here 1 as well. So in these two conditions the guard is in place, but here we have another condition here as well, and switch off logic 0 when the motor is too hot, means this cool will be what, this will be 0. Okay, so this 0 will be here. Okay, and here as well. Okay, so we can see that we have two conditions where this, here we have these two conditions where this is 0. So let me write here the switch will be what, the switch will be off when it is hot. And similarly, in order to see that the guard is also present while the switch is hot, so in this condition we can also make it what, we can make this switch off, because the more priority will be given to the motor switch cool. Okay, similarly here when the guard is not present but the motor is in cool, so as the guard is not present, so I have to switch it off as well. Okay, so these are the conditions, and on the basis of it what I have to do, I have to go towards another step, and that is here the step number 3, and that is step number 3, and that is circuit expression. Okay, so the Boolean expression will be on the basis of this thing which we have found, and on the basis of it what I have to do, I have to collect the element where the output is 1, and from here I can very easily see that the expression here is what, that is guard multiplied by MC. Okay, and that is the output expression. Okay, so we can very easily see that this is the output expression for it, and on the basis of it what I have to do, I have to devise the step number 4, which I am going to write here. Step number 4 is hardware description. Okay, so we can see that here how many gates do we have. So here just one gate, and that is what, that is the AND gate. So let me draw it here by using this color. So, or let me use this yellow color. So we will have just this AND gate which has these two inputs and one output, and this one output is the switch output, and inputs it has our guard and MC. Okay, so when both of them are present, when the switch is cool and guard is present, the output of it will be here. Okay, so that is the overall design process in which we have seen different steps. Okay, the first step here was what? Here the first step was, let me see, writing all the things on in your own language. Okay, so this was basically step number 1. In step number 2, you have to draw the truth table. Okay, so after it we have step number 3. Okay, so in step number 3 you have to write the Boolean expression for the circuit, and for step number 4 you have to write about the digital hardware which you are going to use here in these type of problems. Okay, so that's it for today, in which we have seen the overall design process for the combinational logic circuits, and we will proceed with these type of problems in our upcoming video. Till then, take care of yourself and I will see you soon. Welcome back guys, this is question 9, and here the statement of this question is an AOI and or invert logic chip. Okay, so here we have a logic chip has two 4 input AND gates. Okay, so we have two 4 input AND gates connected to a 2 input NOR gate. Okay, so what we have here, in order to solve it, let me first write that here we have 2 gates, okay, which are of 4 input AND gates. Okay, and we have a single gate, okay, which is what? Which is a 2 input NOR gate. Okay, so we have AND and NOR gate, and on the basis of it we have to write the Boolean expression for the circuit. Okay, so let me first draw the circuit for it. So the AND 4 input AND gates are 2, so let me first draw them. So this is a first AND gate, this is a second AND gate, and as we know that each gate has 4 inputs, so there are 2 gates and each has 4 inputs and 2 outputs. So here we have these 2 gates, 1 and 2, so this is 1, this is 2, and similarly a single NOR gate which has 2 inputs. So this is basically a NOR gate, at the output of it is a bubble and it has these 2 inputs. So let me connect them. First let me write all the combinations. So the inputs to it are A, B, C, D. Okay, so we can see here that assume the inputs are labeled A through Z, so therefore I am writing them A, B, C, D, and here E, F, G and H. Okay, so the output of them will be A, B, C, D all multiplied, and here E, F, G, H. Okay, so now these inputs are given to what? These are given to this circuit, okay, as an input. So when these are given to it, what will be the output here? The output here, let me write it with this blue color, this yellow color as well. So it would be A, B, C, D plus E, F, G, H, and due to the NOR gate it will be whole complemented, and this is what? This is the output expression for our circuit which we had to find out. Okay, so on the basis of the statement we have found out the hardware description, that is the hardware, digital hardware. Okay, and from this digital hardware we have found out the Boolean expression, and from it I can very easily draw the truth table for it as well. Okay, so this is the design process as well. So we have seen some steps of it in our question here. So that's it for today, and I will see you with some more interesting questions in our upcoming. Welcome back guys, this is section 5.2 and today we are going to solve question number 10 of it. So in this question the statement is use AND gates, OR gates. Okay, so AND gates, OR gates, or combination of both. Okay, so the combination of both should be used to implement the following logic expressions as stated. Okay, so we have to implement these logic expression as the digital circuits of the digital logic design, which is the basic step in the digital logic design circuitry. Okay, so here step or the part A here is A plus B plus C. Okay, and that is basically equal to X. Okay, so the first step here is to see what are the inputs we have. So here we have three inputs, A, B and C. Okay, so let me draw them here. This is A, this is B, this is C. So let me label them as well. So A, B, C, and what are basically the what are basically the operations which has been done here. So here the operation is this plus, which means OR. So in order to simplify this question, what are we going to do? We are basically implementing this circuitry or the gate for which the number of inputs will be the same as the number of inputs given in this question. So therefore we are not restricting ourselves to the 2 input gates, but the number of inputs to the gate can be variable. Okay, so what is this? This is basically the OR gate, and here in order to draw it, what I have to do, let me draw it by using this color. So this is the OR gate. Okay, and the inputs to it are this, and this. So let me connect it with this one, and this one, and the output of it is X, which is A plus B plus C. Okay, so what is this? This is the output circuit. Similarly, for part B here, let me write part B here, and the output here is A, B, C. Okay, again we have 3 inputs, so let me draw the number of inputs here. So A, B, C, let me label them A, B, C, and the operation which is performed here is this AND operation. Okay, so let me draw this AND circuit with these 3 inputs. So the AND circuit is represented by this sign. Okay, as the number of inputs are not restricted to 3, so not restricted to 2, so therefore I am drawing the 3 input AND gate. In reality you might have them in the form of the 2 gates as well, and in order 2 inputs as well. So in order to implement then these kind of circuits, what you have to do, if you have 3 inputs, so let me draw them here. So there you will have this gate. So first you will have to implement these 2. So if this is A, B, C, okay, the output of it will be given to the second 2 input circuit. So it will be here, and it will be given to it as well. So here in this manner it will give me A, B, C. Okay, but here as we are not restricting ourselves to the 2 input gates, so therefore all of it, these inputs will be given to this gate, and the output of it would be what? That would be X equal to A, B, C, and that is the output of part B. Okay, similarly in part C, let me move down somehow. So in part C, what we have, so let me write here part C, and in part C we have A plus B, C, and that is equal to X, which is the output. Okay, so let me see that how many inputs do we have. So the number of inputs we have are 3. So again the number of inputs, let me draw them here. Okay, this is here, and let me label them. This is A, this is B, this is C. These are the number of inputs. And what has been happening here, we can very easily see that here first B and C are multiplied together, and then these are added with this A. Okay, so first of all these two will be multiplied together and then added with this A. So therefore we will have 2 gates here, the AND gate. Okay, and this will be what? This will be OR gate. So therefore let me draw them. So the AND gate is between B and C, so this will be the AND gate. Okay, so when this will be given, so what will happen here? Here I will get B multiplied by C. Okay, and after it, what is happening here? This product is added. Okay, this BC is added with this one, so this is the product which is now given to this OR gate. Okay, which has also 2 inputs, so this BC is given to it, and similarly with it this A is also provided, and the output of it will be equal to what? A plus BC, and that is what? This is the answer of part C here. Okay, so here we can see that this is the circuitry which have to be implemented. Okay, similarly for part D, this is part D. So this is the only part which this is the last part of this video, and after it in our next video we will talk about part E, F, G and H. So let me move down somehow as well. So now in this part we have here part D. So in part D, what do we have? So in part D we have AB plus CD. Okay, so again let me first see how many inputs do I have. So here the number of inputs will be 4 and those are AB and CD. So let me draw them here. So let me draw them here. So A, B, C and D, and these are A, B, C and D. These are the inputs. Okay, so what are the operations which has been performed here? Here we can see that in between these two and in between these two we are having the AND operation. Okay, similarly here the AND operation, and in between them then OR will be performed. So first of all these operations will be performed and at the end these will be added together. So let me do the same here. So A and B. Okay, so here these two will be given and here I will get what? AB. Okay, similarly here CD. Okay, 2 inputs and these will be given and here I will get what? CD. Okay, after it these are added together, so therefore here I will have this OR gate with 2 inputs. Okay, these outputs are given to it and here we will get what? AB plus CD, and this is what? This is equal to X, and this is the answer of part D here which we had to find. Okay, so in this video what we have done, we have talked about all the parts from A to D, and we have seen that how to implement the Boolean expressions by using the digital circuitry which we have previously seen, and here all the circuits are composed of AND, or the combination of these two. Okay, so that's it for today, in which we have seen all things which I had to do and which are asked in this question. So I will see you with the remaining parts in our upcoming video. Till then, take care of yourself and I will see you soon. Welcome back guys, this is question 10 and today we will talk about part E, F, G and H, and in previous video we have solved all the questions from A to D. Okay, so let me talk about part E now. So in part E we have word that is X equal to A plus B and C plus D. Okay, so here what is the first step? As we have previously seen that we have to see the number of inputs. So the number of inputs we have here are 4 and those are A, B, C, D. So the inputs we have are A, B, C and D. Okay, and let me draw them. These are the input lines. Okay, and what has been happening here, we can see that C and D are added together, A and B are then added together, and this bracket means this operation will be performed first, and at the end what will happen here, we will have to multiply them, and that is the AND circuit. So therefore we have two OR circuits in which A and B are added. Okay, and then C, D are added, and at the end these are combined by using this AND gate. Okay, so let me first draw two OR gates. This is a first OR gate with 2 inputs and this is a second OR gate with 2 inputs as well. To it what is given, A and B are given and the output of it will be A plus B. Okay, to it what is given, this one and this one, and to it the output would be C plus D. Okay, when we have obtained A plus B and C plus D, okay, these are ANDed together by using this AND gate and the output of it is X, and to it 2 inputs are given which are these one. Okay, we can see that these are the inputs which are given to it and these are A plus B multiplied by C plus D. Okay, so that is the solution of part E here. Okay, similarly for part F what we have, so let me write part F, and that is x equal to a plus b c d. Okay, so as I have previously stated that I'm not restricting myself to the two inputs gates, but here I will solve it by using the two possible combinations in which if I don't have the two input gates and in which I have only the two input gates. So here what are the steps? First of all, I have to see the number of inputs. So number of inputs are again 4. So the number of inputs are a, B, C, D. Okay, and these are 1, 2, 3 and 4. Okay, so what has been happening here, if I don't have the only two gate inputs but any number of inputs I can use for a gate, so therefore in that case here B, C, D are multiplied together and at the end these are added with this A. So therefore here I will have the AND circuit. Okay, here I will have the AND circuit which is then ORed with this A. So therefore this is the AND with 3 inputs. Okay, sorry, I have to use the color which is here. So this is having 3 inputs. Okay, so this is a first, second and third, and the output of it will be B, C, D. Okay, and this with it what I have to do, this will be the OR circuit, and to it two inputs are given. The first one is here and the second one is here, and therefore the output of it will be A plus B, C, D, and that is what, that is the output of it. Okay, this is the first combination in which I don't have the two input gates. Similarly, for the case when I have only the two input gates, what I have to do here, the inputs will be the same A, B, C, D, and these are here. Okay, so initially B, C, D will be multiplied together because the only gate I have is of two inputs. So therefore the output of it will be what? The output of it will be BC, and this BCD has also been multiplied with this D as well. So therefore the two inputs, okay, this is given to it, and to it this one is also given. So what I will get here, I will get this BCD. Okay, so this is the gate which I have, and at the output of it what I have to do, this will be X, and to it the two inputs are given. Okay, so one is here, so let me write here as well, and the second one is this one as well, and this X will give me what? This will be the same as A plus B, C, D. So these two are the different combinations. This is for the only two input gates, and this is for the variable number of inputs. Okay, so this is more practical because most of the gates which we will see in practical will be of two inputs. Okay, so therefore we have solved it like this. Okay, so today we have solved these two questions E and F, and I hope this is now understandable that how to implement these by using the AND or the combination of them. So in our next video we will talk about part G and H. So I think it's enough for today, and I will see you in our upcoming video. Thank you. Welcome back guys, this is section 5.2 and we have solved all the questions from part A to part F. Today we are going to talk about part G and H. Okay, so let me talk about this G part, and here we have X equal to ABC plus BCD plus DEF. Okay, and here again we are not restricting ourselves to the two input gates, but three input gates are also possible. So first of all, the step is to see how many inputs do I have. So the inputs we have are here, so all the variables or domain of it is A, B, C, D, E, F. So I will have A, B, C, D, E and F. Okay, so these are 1, 2, 3, 4, 5, 6 inputs. Okay, so the lines, input lines are here, Okay, so we have here 6 inputs. Okay, so what are the operations which I have to perform here? So here we can see that here DEF will be multiplied together, and the first gate here will be and. Okay, here BCD will also be multiplied together, and here I will have AND gate here as well, and here ABC is also multiplied together, and here I will have this AND gate. At the end, these blocks, this and this, these will be combined together by using a single OR gate. Okay, so let me draw them here. So the first gate here is between A, B and C, so this is the AND gate. Okay, so here 3 inputs. Similarly, the second gate is also 3 input AND gate, and the third gate is also this 3 input gate. So the inputs and these are the outputs. Okay, so the output of the first gate is ABC, so let me give them A, B and C, so therefore the output of it will be ABC. Okay, similarly the output of second one is BCD, so this will be B. Okay, this is C, and here this D, so here I will have BCD, and to the third gate I have here DEF, so DEF, so D, E, and here this what F. Okay, so I have here D, E, F, which are at the end combined together by this OR gate. So let me draw this OR gate, and this is the OR gate with 3 inputs. Okay, so to the first, let me use another color with it, and this is, let me use this one. So this is the first input, this is the second, and to it I am going to use this third one, and this is the output, and this output is composed of ABC plus BCD plus DEF, and that is the output of this circuit. Okay, so here I have seen that how to implement this part G as well. Okay, similarly for part H, what I have here, let me move down somehow. So part H, how many inputs do I have? So let me first write the statement for it. So the statement for it is H, and that is ABC, and with it I have to multiply with D plus E plus F. Okay, and with it plus AC, and with it I have to multiply C plus D plus E. Okay, so again the number of inputs are also 6, because I can see that these are composed of A, B, C, D, E, F. So here A, B, C, D, E and F. Okay, so these are 1, 2, 3, 4, 5, 6 input lines. And what are the operations here which I have to perform? Okay, so the first operation, as the bracketed operations will be performed first, so the first operation which will be performed is this one and also this one, because here D, E and F will be added together, and here C, D, E are added together. So let me first add C, D, E. So these will be added together by using the OR gate. Okay, so C, D, E are here, so let me add them by using a 3 input OR gate. Okay, so here C, D, E, and here I will get C plus D plus E. Okay, and similarly here D, E, F. So for D, E, F, let me use another OR gate. Okay, so this is the OR gate, and to it 3 inputs. So D, for the D, what I will have here, for D I have this input. Okay, for E I will have this, and for F I will have this one. Okay, so here I will get D plus E plus F. Okay, so these are the 2 inputs. With this CDE, the multiplication term is AC, Okay, so first of all AC will be multiplied together, and with it I have to multiply this term as well. So as I am not restricting myself to the 2 input gate, so therefore let me use this one here. And for the third step, this is a 3 input circuit, and to it I have here what? This is A, this is C, and with it I have this one. So what I will get here, AC multiplied by C plus D plus E. Okay, and similarly here I can see that ABC is multiplied with DEF, so therefore ABC is 3 input with this fourth one is also here. So I will have here this 4 input AND gate. So 1 2 3 4. Okay, ABC will be, A will be here, this is A. Okay, with it I will also have this B, and for C let me move down from here. Okay, this is C, and this gate, this is DEF. So from here what I will get, let me write it here. So ABC, and with it D plus E plus F. Okay, so here the output is this one. Okay, these are the outputs, and at the end these are combined together by using this OR gate. Okay, we can see that these are combined together, this one and this OR block is combined together by this OR gate. So therefore this is the OR gate, and the output of it will be X. So it has 2 inputs, one is this, okay, the other one is this one. Okay, so that is the output of this circuit. So the X will be what? This will be the combination of AC, C plus D plus E, and ABC, D plus E plus F, and this is the same thing which we have in part H. Okay, so that is the hardware implementation of part H. Okay, so that's enough for today, and here we have seen that how to solve more complex parts of our question, and here we have solved them by using the easier method, which is to formulate the strategy first, first of all seeing the number of inputs, and then starting from the lower to the higher level of abstraction. So that's it for today, and I will see you with other questions in our upcoming video. Thank you so much. Welcome back, guys. This is question 11 of section 5.2. okay, and today again we are going to talk about the implementation of combinational logic circuits. In this question we are asked that use AND gates. Okay, so we have to use AND gates, OR gates, and inverters, okay, or the combination of these 3 gates as needed to implement the following logic expressions as needed. Okay, so here today we are going to talk about the first 3 parts, okay, and in our next video we will talk about the remaining parts. So here part A is X equal to AB plus B complement C. Okay, so what is the procedure here? In order to proceed here, what I have to do, first of all I have to look for the inputs, at how many inputs do I have here. So here I have 3 inputs, and these inputs are A, B and C. Okay, so let me first write them here. So I have A, B and C, and the input lines are here. The input lines are A, B and C. Okay, so what are the steps here? I can very easily see here that, let me use this color for it. So I can very clearly see here that here AB is multiplied together, and here B complement C is multiplied together. But here before the multiplication of BC, what I have here I have the complement of B. Okay, so I have to use here NOT gate, and after this NOT gate these two are ANDed together. Okay, similarly these two are again ANDed together, and at the end what will happen, these will be ORed. Okay, so these two will be combined by using this OR circuit. Okay, so let me first start it from here. Okay, so AB is multiplied together, so here I will have the AND gate, and that is this one, 2 input AND gate. Okay, so the output of it is here, and the inputs to it are this and this, and here I will get AB. Okay, similarly to the other gate, I have here another AND gate, and this is here 2 input AND gate. Okay, but here is a difference to it. To one input C is given, while for the others input I have here B complement. Okay, so in order to proceed here, what I have to do, I have to complement this B, and to it I will get here B complement. Okay, so what I will get here, I will get B complement C. Okay, so these are what, these are the AND gates and this NOT gate which has been implemented here. And after it, in third step, what I have to do, let me use another color for it, and for it I am going to use this orange color. Okay, so this is another OR gate, and for this it will be implemented here. The A, B and B complement C are combined together by using this OR gate. So this OR gate is here 2 input OR gate. Okay, to it first input is this one, second is this one, and the output of it is X equal to AB plus B complement C. And what is this? This is the output which I wanted to find out. Okay, so this is the implementation of part A here. Okay, similarly for part B, what I have here B is what, so let me write it here, let me move somehow here. Okay, so here the input what I have here is, that is the expression, and the expression for it is X equal to A B plus C complement. Okay, and for it, let me first see that how many inputs do I have. So I have 3 inputs. Okay, so these are here, let me draw them here, A B C. Okay, and the input lines are here, here and here. Okay, first expression, what I have to do here, I can see that what I have to do, I have to combine B and C complement, because this is now bracketed and therefore I have to combine them first. But here I have the C complement. Okay, so what I have to do here, I have to use the NOT gate, and after this NOT gate, these two are combined by this OR gate. Okay, so therefore first of all, what I have to do, I have to take the inversion of this C, and here I will get C complement, and then this B and C complement are combined together. Okay, so here these are combined together, and here what I will get here, B plus C complement. Okay, so here I have it. So after it, let me use another color, and this color is here, and after it, what will happen, this and this bracketed one are ANDed together. Okay, so here I have to use the AND gate, 2 input AND gate, and the output of it will be the combination of these 2 inputs. So here I will have A multiplied by B plus C complement, and this is what, this is X, and this is the required output which I had to find out. Okay, so this is what, this is the required output. So this is the answer of part B here. Similarly, now in order to proceed to part C, okay, so let me proceed to part C here. So part C here is this, and here what is part C, that is X equal to AB complement plus AB. Okay, again the same procedure I will follow. I have to see that how many inputs do I have here. So I have 2 inputs, so the 2 inputs are A and B. Okay, and what I have to do here, A and B complement are multiplied together, so, and here A B are multiplied together. So here this is the NOT gate, and after NOT gate, these two are ANDed. Okay, here these two are ANDed together as well. Okay, so here what will happen, So let me use this line for it, and first of all let me have this AND gate. Okay, so this is what this will be AB, and with it I have to use another AND gate, and to it the inputs will be A and B complement. Okay, so for A it will be here, it will be A, and for B I will have what, this will be the inverter, and here I will get this B complement, and therefore I will have here AB complement. Okay, so after what I have to do, I have to combine them by using this OR circuit here. So OR gate here will be like this one, two inputs. Okay, so two inputs are here, and the output of it will be then AB complement plus AB, and this is the required output, and the circuit for it is also here, and this is the solution for part C here. Okay, so that's it for today, in which we have seen three parts. The part A, okay, this is part A, part B and part C, and we have seen the combinational logic circuits for them. Okay, so I hope you have understood all the steps which have been carried out here, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So if in our previous videos we have seen the solution of first three parts of question 11. Today we are going to talk about part D and E. Okay, so let me start from part D here, and here we have the expression, and that is x equal to a b c whole complement plus b, and with it I have e f plus G complement. Okay, so first step here is again the same, that I have to see that how many inputs will I have. So the domain of it is A, B, C, D, E, F, G. Okay, so I have to write them here. So the domain of it is, let me write it here, A, B, C, D, E, F and G. Okay, so this is G, and let me draw lines for them. These are the input lines. Okay, so we have these input lines. Okay, to it I can very easily see that here we have this expression and then this expression, and these are combined together by this OR gate. And again I am not restricting myself to a two gate circuit, so therefore I can use any number of inputs to a gate as possible. So here I have ABC and the complement of it. So let me use this first gate, and that is the AND gate here. So the AND gate here is here. Okay, and to it first input is here, second is here, and third one is here. So the input to it is A, B, C. Okay, and what I will have here, I will have here A, B, C, and what I have to do, I have to invert it. So therefore I am going to use this inverter here, and therefore what I will get, A, B, C whole complement. Okay, so this is the first input which I have here, and this is here, this one. After what I have to do, here I can see that here the second part, and here I have B and E, F, G complement, while here I have to first multiply E and F, and with it I have to add the G complement. So let me start it with this multiplication which is inside of these brackets. So let me start with this multiplication. So E and F are multiplied together, and here I have to use this AND gate. Okay, so this is E and this is F, and the output of it is EF. Okay, and with that this G complement is what, this is added. So therefore I have to use here this OR gate with two inputs. Okay, so to this one input this EF will be given, while to the second one this G which is inverted. Okay, so I will get here G complement, this will be given, and here I will get what, this will be EF plus G complement, which is a part. Let me write it with this one. So this is here. Okay, with it I have to multiply what, this b. So here I have this one, and with it I have to multiply this b. Okay, so therefore let me use this color, which is, let me use the same color here. So the color here is this one, and this is again a 2 input AND gate. Okay, so here I have to multiply this one with what, with b. Okay, so I have here, this is b which is given to it, and what I will get here b ef plus g complement. Okay, so now I have these two inputs which are two separate parts. First part is here, this is a first part, while this one is the second part, and these are combined together by this OR gate. Okay, so let me draw a final OR gate with this blue color. So this is a 2 input OR gate, and to it one input will be ABC whole complement, and the second one is this one, and the output of it will be what, ABC whole complement plus B EF plus G complement, and this is the solution for it which I had to find out. Okay, so this is the solution. Interesting thing here is that we can see that here we have first described that we will have these number of inputs, but here we can very easily see that D is not used. So as the domain of it was first composed of these 7 inputs, but as D is not used, so therefore I have to see that which variable which is not available here, I have to remove it in the first step. Here I have solved it, and to show you that this is in between them and it is not used, so therefore I will not use it either, but the domain of it will be composed of A, B, C, D, E, F, sorry, A, B, C, E, F, G. Okay, so these three and these three, these will be composed of the domain of it. Okay, so this is the solution of part D here. Okay, similarly for part E, let me move around somehow. Okay, so for part E here, let me write the statement for it, and that is x equal to A B C A plus B plus C plus D. Okay, so here I have this question. So what are the steps here? The first step is to see how many inputs do I have here. So again, the number of inputs are 4, A, B, C and D. Okay, so let me solve it by moving somehow downward. So this is here, so let me start solving it, and to here the number of inputs will be what, let me start solving it here. So A, B, C and D, and these are 1, 2, 3, 4. Okay, so what is the first step? I can very easily see that here in this bracket these 4 are added together, and then these are multiplied with this BC. Okay, so here these BC are added together. Okay, and these are OR together. Okay, so let me use different color for them. For it I'm going to use this color, and for it I'm going to use OR. Let me use the same color for it. So the same color for it will be, for the A plus B plus C plus D, I am going to use this OR gate. So this OR gate will be here with 4 inputs. Okay, so 1, 2, 3, 4, and the output of it will be here. So to it I will have this one, A, B, C, okay, and D, and the output of it will be A plus B plus C plus D. Okay, and with it I will have BC. So BC is this AND gate, and to it I have 2 inputs. So BC will be, this will be here. Okay, so this is B and this one is here. Okay, so these are the 2 inputs taken from it, and I will have here BC. Okay, so now we can see that very clearly that here I have B while here I have C, and these are multiplied together, which can be seen here, and this is by using this AND gate. Okay, so here I have to use a 2 input AND gate, to which I will have 2 inputs. This is a first input, this is the second input, and to it I will have here the output of it will be BC A plus B plus C plus D. Okay, so this is what, this is the overall thing which is here, and this one is now here. Okay, with which I have to multiply here A, and this is another AND gate with the different color I am being using here. Okay, so another AND gate, and to it the output of it will be here. The 2 inputs are applied here. The first one is here, the first input will be here, while the second input, which is A, will be, okay, this is here, and here I have A, and the output of it will be X, and X will be the product of this and this, and the output of it will be what? X will be A multiplied by BC multiplied by A plus B plus C plus D. Okay, and that is what, that is the output which I wanted to find out here. Okay, so this is the solution for our question, and we have seen the circuit implementation for the expression which is given here. Okay, so that's it for today, in which we have seen the solution of two parts of our question. Welcome back, guys. So this is question number 12, and previously we have solved part A of this question. Today we are going to solve part B of it, and also part C. Okay, so what is part B here? So in part B we have A, B, C prime, D prime, okay, plus D, E prime, F plus AF whole prime, and this is equal to X. And what are we asked to do? We have to use NAND gates, NOR gates, or combination of both to implement the logic expression which has been given here. Okay, so first of all, let me see that how many inputs do I have. So here I have A, B, C, D, E, F here. So let me write them here, and for it I'm going to use this color. So I have A, B, C, D, E, and F. Okay, so these are the inputs we have, and writing or drawing the input lines from here. Okay, so here we have, first of all, let me implement this one, and writing this one, what I have to do, first of all I have to multiply these 4 terms, and before multiplying them, what I have to do, I have to take the complement of C and D. Okay, so therefore let me first use this NAND gate, okay, with it, and giving this to it, what I will get here C complement. Okay, similarly another NAND gate, okay, this will have 2 inputs, combining these 2 inputs and giving this to this one, what I will get here, I will get here D complement. Okay, so now as we have got these all, so let me use another NAND gate here with 4 inputs. So okay, so 1 2 3 4. Okay, so to these 4 inputs, let me give first A, then B, then okay, then C complement to this one, and also to this let me give this D complement, or let me draw them here as well. So this is D complement, and at the output of it, what I will get A, B, C complement, D complement, and the whole complement of it. And in order to remove this whole complement, what I have to do, I have to use another inverter here, and this inverter will also be the NAND gate with 2 inputs connected together, and at the output of it, what I will get A, B, C complement, D complement. Okay, so this is the first term which I had to find out. Similarly, now what I have to do, I have to find out this second product, and that is DE complement F. Okay, so first of all, let me complement this E as well. So complementing this E using this NAND gate with the two inputs combined together. So therefore here I will get this E complement, and after it, as I have DE complement F, so let me use here another NAND gate. Okay, sorry, let me use it here. So here this NAND gate, okay, and with this let me have these three inputs, and here I will have this D. Okay, so let me use this D here. Okay, this is D given to it, and to the second input let me give this E complement, and to the third let me give this F. So at the output of it, what I will get D E complement F with the whole complement. And in order to remove this whole complement, what I have to do, I have to use another gate or NAND gate here, to which I have to apply this input, and at the output of it, what I will get here D E complement F. Okay, so this is the second part which I have here. Similarly, now in order to implement this third product, which is AF whole complement, so what I have to do, I have to use the NAND gate here and the simple inputting the inputs A and F to it, but I will get my answer. So let me get this NAND gate to this. I have two inputs. Okay, one will be the A and the second will be the F. So this will be A here, this is A, while this will be the F. Okay, so at the output of it, what I will get here AF whole complement. Okay, at the end, what I have to do, I have to add them together. So therefore let me use the NAND gate, because the NOR gate, because I cannot use other than NAND and NOR gate. So let me use the 3 input NOR gate, and to them let me apply the inputs. Okay, so at the output of it, what I will get here A B C complement D complement plus D E complement F plus A F whole complement and the whole complement of it. What I have to do, I have to remove this whole complement. So therefore let me use another NOR gate. Okay, I can also use here the NAND gate as well, but here let me use this NOR gate, and to this NOR gate let me apply the same input. Okay, so at the output of it, what I will get, this complement will be removed. Okay, and at the output of it, what I will get A B C complement D complement plus D E complement F plus AF whole complement. Okay, so this is X, and that is the answer of my question, which I had to find out here. Okay, so that is the solution of part B here. Similarly, you can also use the same procedure to find the solution of part C here as well. So I am giving it for this part C for your own practice here, and I am not solving it, but this is the solution. You have to perform the same steps I have performed here. If you want to invert any input, what you can do, you can either use the NAND gate or NOR gate with the 2 or 3 inputs combined together, then the same input will be applied, and similarly the other gates will also be implemented by deploying the same methods which we have previously covered in our introductory video of the NAND and NOR equivalent gates. Okay, so I think it's enough for today, and I will see you with some more interesting questions in our upcoming video. Take care of yourself, and I will see you soon. Welcome back, guys. This is section 5.2, and today I'm going to talk about question 13. So here the logical circuit has been given in the form of table 5.8, which is basically the truth table. Okay, so what is this statement here? Implement a logic circuit, okay, for the truth table in table 5.8. So this is table 5.8, to which different inputs and a single output has been given, and for it I have to implement the logic circuit. Okay, so let me solve it. So solution for it. So the first thing here is that I have to see that what is the domain of it. So the domain of it is composed of the inputs. So I have here A, B, C, and for these inputs I have to calculate the sum of product form. So SOP form for it will be what as I have previously shown you guys that what I have to do, I have to select all the inputs or the terms for which the output is 1. So this is first, this is second, this is third, fourth and fifth, and I have to make each product equal to 1 by complementing them and then adding them together. So this is a first term here, so 0 0 0, and here I have to make it what that would be A complement, B complement, C complement. Okay, the second term here is here, so here A is 0, B is 1 and C is 0. So what I have to do, I have to write it A complement, B is 1, so the product it will not affect, and therefore C should also be complemented to make it what 1. Okay, similarly the third one is 1 0 0, so here A is not 0 and B and C are 0, so therefore I have to complement them. So A, B complement, C complement. Okay, the second last one here is that A, B, C, so that is 1 1 0. So what I have to do, I have to make it A, B, C complement. Okay, and the last one is 1 1 1 because for it the output is also 1. So that would be what? That would be A, B, C. Okay, so after it what will be the step? I have to add them together in order to get these output of it. So that would be the summation of them, and that is what? That is the sum of product form for my question, and it is now very easy to implement them. Okay, so it will be the same way in which I was basically implementing all the circuits for which the expression or the Boolean expression was given. So here what is the first step? I have to see the number of inputs. So the number of inputs for it, I have number of inputs I have are 3, and those are A, B and C. Okay, and the domain of it is also this. So let me move somehow here. Okay, so let me move down here and let me now write these inputs. So here A, B, C, and these are 1 2 3. Okay, so the first expression, let me draw them by using the color which is here, or let me use this white color for it. Okay, so that is A complement, B complement, C. So in order to complement it, what I have to do, in order to complement, I will use the gate which is the inverter. So to inverter I will have here. Okay, so the outputs of these inverter are A complement, B complement and C complement. Okay, these are the outputs of it, and the after this inversion I have to what add, I have to multiply them because A complement, B complement, C complement are multiplied together. So let me multiply them, and for it I am going to use this color. So to it the three inputs are 1 2 3, and the output of it will be here. So it will be here, here and here, and the output of it will be here. And let me write it with this white color: A complement, B complement, C complement. Okay, the second term here is A complement B C. So the second gate is again AND gate. Okay, so this is the AND gate 1 2 3, and to it A complement, B and C are given. So the A complement will be here, okay. C complement will be from here, while B will be from here, okay. So what I have to do, these are the outputs of it. So here I will have A complement B, C complement will be the output, okay. For the third term here I will have A, B complement, C complement. Again I will have the third AND gate, okay. So three inputs are here, and here I have A, B complement, C complement. So C complement is here. So first let me draw this A, okay, because this is uncomplemented, so this will be here, okay, and the other two terms are now complemented. So this is what, this is a second term, so let me draw from here to here, this is here, and the C complement is here, okay. So the output of it will be again with this color, so A, B complement, C complement, okay. Let me move somehow down as well, okay. So here this will be what, the other gate will be here, and here I will have again three inputs, and to this gate I will have here A, B, C complement. So A and B are both here, so let me use this A for it here, B for it uncomplemented here, and C is complemented. So therefore what I am going to use this here, so it will be here, and what I will get here, I will get here A, B, C complement, okay. And the last gate here is for it, that is now this ABC, okay. So let me move down, and after it what I will do, I will add them all together. So this is will be the expression, and I am going to implement it here. So let me move down somehow as well, okay. And here the last gate is this 3 input AND gate, and to it ABC is given. So A is again here, B is from here because these are uncomplemented, and C is again here, sorry, and C is here, okay. So these are here, and the output of it will be ABC, okay. So now I have to add them together, and to add them what I will have to use, I have to use the OR gate, and to implement OR gate I will have here, and this will be what, it will have 5 inputs, so 1 2 3 4 5, okay. To it the first input is this one, to it the second is here, the third one is here, this is the fourth one, while the last one will be here. And this is what, this is the output which I wanted to find out here, and this is the same output which I had here, and here it is A complement, B complement, C complement plus A complement, B, C complement plus A, B complement, C complement. Let me write others here. So A, B, C complement plus ABC, okay. So what is this, this is X, and this is the required expression which I had to find out, and this is the solution of the question which I had here, okay. So that's it for today, in which we have seen the solution for question number 13, in which first of all the table or truth table is converted to the SOP form, okay, which is now mentioned here. So this is what, this is the SOP form, the table is first converted here, and then after finding the domain of it, all of it is now converted into the circuit which can be seen here in this form, okay. So it is now very clear that this is the implementation of the expression which is given. So I hope all the steps are now clear to you guys, and I hope to see you guys again with another very interesting video which will demonstrate the solution of other questions of this section. Welcome back guys, this is section 5.2 2 again, and here we are implementing the combinational logic circuits. Okay, so question number 4. Okay, implement a logic circuit for the truth table in figure 5.9. so this is the table in figure 5.9, and here we have to implement it in the form of a logical circuit. Okay, so the logic circuit comprised of all the inputs which it has, and it will give us the output in accordance with the inputs which are given to them. Okay, so first of all, let me see how many inputs do I have here. So I have here the 4 inputs, and those inputs are A, B, C, D, and that is also the domain of it. Okay, after what I have to do, I have to find the Boolean expression for it. So to find the expression of it, what I have to do, again the same procedure, I have to see that what are the outputs for which I have got 1, and have to select the inputs for them and then write them in the form of the sum of the product forms. Okay, so let me see what are the inputs to which, what are the outputs to which the inputs are given. So the outputs for which it is 1, so this is 1 here, and for it the input is here. So this is 0 0 1 0. Okay, so in order to write the expression, what I have to do, I have to write it in the form of the product which give me 1. Okay, so here I have 0 0 1 0, so therefore it will be A complement, B complement, C and D complement. Okay, so this is the first one. In second one, I have this one, and for it I have 0 0 1 1. So it will be what? It will be 0 0. So A complement, B complement, C D. Okay, the third one here is 0 1 0 0. So 0 1 0 0 will give me A complement, B, C complement, D complement, because I can see that only B is 1 here while all the 3 are 0. So in order to make this product equal to 1, all of them should be equal to 1. So therefore I have complemented the 0 terms. Okay, similarly here the output for which the inputs for which the output is 1, so here it will be 1 triple 0. So 1 triple 0 is A, B complement, C complement, D complement. Similarly here this one 1 0 0 1, so 1 0 0 1. Okay, this one here, and this one for which I have got 1 is 1 0 1 0. So 1 0 is complemented, 1, and this is complemented as well. The second last one is 1 0 1 1. So 1 0 is complemented, 1 0 1 1, and the last one here is all ones. So A, B, C, D. Okay, so this is what, these are all the terms for which the output is what, the for which the output is 1. So what I have to do, I have to add them now in order to make it the product of the sum form. So addition of them will give me plus, with it this will be added, and these are the terms. Okay, so this is what, this is the product sum of the product form. So this is the required SOP form. This is for the expression of this truth table, okay, which we had to find out. Okay, after finding it out, what I have to do, I have to implement it, and in implementing it, what I have to do, I have to see that how many inputs do I have. So the number of inputs I have are 4. So those are A, B, C, D, and these are 1 2 3 4. Okay, so these are what, these are the inputs. So let me extend them as well because I will be needing them. So these are here. Okay, now I have got these ones. So what is the first term here? The first term here is, let me use this white color for it. So the first term here is A, B prime, C, D prime. So this is the A, B, C, D prime, and I know that I will be needing the complement of them as well. So let me first complement each one of them by using this inverter. Okay, so the inverters are here. Okay, so these are the inverters, and here I will get A complement, B complement, C complement, and D complement. Okay, so after it, let me use this white color for all the gates, okay, or yes, this white color for all the other gates. So here what I will get, this is A, B, C, D, and the first as I have 1 2 1 2 3 4 5 6 7 8 number of the products, so let me use the 8 number of AND gates, okay, 1 2 3 4 5 6 7 and this is 8, and each one of them has 4 inputs, okay, here as well, here as well, here 4 inputs, okay, and a single output from here. So these are the single outputs. So what I have to do to each of them, I have to give some inputs. So let me use the color which is this one. So here for the first one I will give A complement, B complement, C, D. So A complement here will be this one, B complement will be this one, okay, and C is uncomplemented, so therefore here it will be, and then the D complement, okay. So here I will get this D complement here as well, and here the outputs of them will be A complement, B complement, C, D complement. To the second one I have to give A complement, B complement, C, D, okay. So let me use them. A complement will be here, okay, the B complement to the second one, and then CD, okay. This is the CD, this one is C, while the D is also here, okay. So what I will get here, I will get A complement, B complement, CD, and this is the output of the second gate. For the third one I have to provide it A complement, B, C complement, D complement. So the A complement here will be, let me use the same one here, B is what, so let me use this B from here, okay, this one, and C complement is what, C complement is from here, okay, and then the last one is D complement as well. So the D complement will be from here, okay. So what it will be, it will be A complement, B, C complement, D complement. For the fourth gate I have here these inputs, and these are A, B complement, C complement, and D complement, okay. So the A here is, let me use this one here, and this one will be here A, okay. B complement is where, so let me use this B complement, and here it is, okay. So let me use this B complement, and C complement is, let me use the C complement which is here, okay, and the D complement term, the complemented term is, will also be here, okay. So this one is the complemented term, and here I will get A, B complement, C complement. The fifth term here is A, B complement, C complement, D. So the A here is what, let me use it from here, okay. This is A, this is A, and B complement is from where is the B complement, the B complement is also from here, okay. This is B complement. C complement is from here. So let me use this one here. This is the C complement, and then at the end I have to use the D. So D is from here. Okay. So let me use this D. You can see that how complex the process is. This is the same procedure which is used inside the circuits, and you will see a lot of wires just like this one. So this is also a practice for that as well. Now the sixth term is A B complement C D. So let me first use the A. So A is here, okay, then B complement. So the B complement term is also here. So let me use this B complemented term here. In order to simplify it, let me also write the second last expression, and that is A B complement C complement D. Okay, and this is A complement B complement C D. A B complement C D. So where is the C term? So let me use this C term here directly from here. Okay, so it will be here. Okay, so this is what, sorry, let me redraw it. So here I will be having it from here, and the last term here is D. So D is again here. Okay, so what is the output? So A B complement C D. Okay, the second last term is here, and that is A B complement C D. So the A will be from here, okay, and B complemented term, okay, I think I have made a mistake here because here it was the D complement, it was, I have made a mistake here, and this was here the D complemented term. Previously I have used this one, so let me use this one here. So I have already used this one which is here. So let me now implement A B complement C D complement. So A is here, B complement is where? So this is the B complement, okay. C is here, which is also the same one. So C is also here. Now I have to use the D complemented term, and the D complemented term is here. So here I will have A B complement C D complement, okay, and the last one is A B C D. So A B C D, for A B C D what I have to do, A will be from here, let me use A from here, B from where? So let me use this B from here, okay, and C from C and D from here, okay. So let me use this C from here and D from here. So D here will be, okay. So what is this? This is basically the implementation of all the products. Now at the end what I have to do, I have to add them all together, and for the adder let me use this circuit, okay. And here how many input do it have? So 1 2 3 4 5 6, this is 7 and this is 8. So let me add them together. This is the first one, okay, this is the second one, let me redraw it, this is the second one, the third one is here, this is the fourth one, fifth one, sixth one, okay, this is the seventh one, and the last one is here, okay. So the output of it will be X, which is what, which is this expression which I had to find out, okay. So what is this? This is the solution for the question 14, in which we have seen the implementation of all the gates. So I hope it is now understandable, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back guys, this is question 15 and here we have to simplify the circuit in figure 5.57. okay, so this is figure 5.57 and we have to simplify it as much as possible. okay, so the simplified term should be as much as possible and we have to verify that the simplified circuit is equivalent to the original by showing that the truth tables are identical. okay, so we have to draw the truth tables of them as well. So let me first write the expression for them. okay, so let me first write the expression for my circuit here. So here I can see that the output here is AB. okay, while here to this gate 3 inputs are given A, B, C and the output of it is A, B, C and X here will be the summation of them. So the output of it here will be AB plus ABC. okay, so this is the expression which I had here and this is equal to X. okay, we can also convert it to the standard form by multiplying this term with the C plus C complement. So X will be equal to AB C plus C complement and here I will have ABC and the output of it will be X equal to ABC plus ABC complement plus ABC. okay, we can see that these two terms are identical. okay, this one and this one, and according to the rules we can see that the ABC plus ABC is equal to ABC. so therefore the output of X will be ABC plus ABC complement. okay, so this is the expression of the circuit which is given. So this is the expression of the circuit which is given in figure 5.57 and this is in standard form. So let me write the truth table for it. So in order to write the truth table I have 3 inputs and these are A, B, C and the output of it is X. okay, so this is basically a truth table and let me write different combinations. So 0 0 0 0 0 1, okay, 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and the last one is 1 1 1. okay, so this is the truth table for it, and from this expression I can very easily see that the output will be only 1 for the binary values which I can calculate here, and those binary values are 1 1 1 and 1 1 0. okay, so for them the output will be what? The output will be 1. so these are the last two values and all the other values will be what? 0. So this is the truth table for the circuit given here. okay, after it what I can do here, I can also simplify this expression by using two methods. One is the conventional method and this conventional method is based on the Boolean algebra rules, and the second method which I can use is the Karnaugh map. So here I am going to use the first method. You can also apply the Karnaugh map method as well, but here I am going to use the first method, and here I can see that this is the expression, and from this expression in two expressions this AB, let me use this blue color for yellow color for it, this AB is common in between them, and I can see that taking it common what I will get here C plus C complement, and according to the rules of the Boolean algebra what I have, X plus X complement is always equal to 1, and therefore the output of it will be what? The output of it will be X equal to AB multiplied by 1. okay, so the output of it will be X equal to AB. Okay, so this is what, this is the final expression or the simplified term, and we can very easily see that the expression here is just showing me that the two inputs when given, it will give me the output which is the product of the two, and this can be implemented by using the, if I have two inputs and these are A, B, and these are given to this AND circuit, and here I will get x equal to AB. This is the output which I wanted to find out. Okay, so this is the simplified version. Now I have to see that how come these two are identical, and drawing the truth table for this expression, I have here A, B, and the output here is x. So 0 0 0 1 1 0 1 1, this is the verification. So in order to verify it, I will get that this is 0 0 0 1, and this is the truth table of this AND gate. Okay, so this is inside this AND gate that I can get this one. Similarly here in this circuit, I can very easily see that I will get the outputs equal to 1 only when the values of A, B are both are 1s, and in other scenarios when any one of them is 0. Okay, I can see that in the first two both are zeros, in the second, in the third and fourth only A is 0, and in fifth, sixth B is 0. So in any of that condition, I can see that it is not seeing that whether the input C is 1 or 0, but it is giving me the output equal to 0. But in the scenario when both of them are equal to 1, the output of it giving me 1, and this is honestly and very easily I can see that this is the functionality of an AND gate. Okay, so therefore it is verified that the output which is given here is the answer. So that is the verification stage in which I have got that the output here x equal to AB is the output which I had to find out, and the truth tables here and here, these two are identical. So that's it for today, and in which I have solved question 15, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself. Welcome back, guys. So this is question number 12, and today we are going to solve the equations by using only the NAND and NOR gates as we have mentioned here, or the combination of both to implement the following logic expressions. Okay, so we have three parts, A, B and C, and today we are going to solve part A. Okay, in previous videos we have seen that how to make the equivalents of different fundamental gates by using the NAND, NOR or combinations of both of them. Okay, so today we are going to deploy the same concepts which we have studied in the previous videos, and by deploying that we have these equations and we are going to implement them. Okay, so in part A we have the expression in which we have A prime B plus CD plus A plus B whole complement ACD plus BE whole complement. Okay, so how are we going to proceed here? Here in all the circuits we have to see that which is the feasible gate which we have to implement here, and we have to choose from the NAND and NOR gate that which is feasible for us. Okay, so here we have how many inputs do we have? So we have A, B, C, D, E. Okay, so let me write them here. We have here A, B, C, D and E. Okay, so these are the inputs and I am going to use the same color for them. So here we have 1, 2, 3, 4, 5. Okay, so these are the inputs. First of all, let me implement this one. So this is A prime B. So I have to first complement B and then multiply it with B. So what I have to do, let me deploy here the NAND gate. Okay, so the two ends of this NAND gates are combined together, and here we will get A complement. Okay, so after this A complement, A and B has to be multiplied together. To multiply them, I am going to use another AND gate. Okay, so here this is the AND gate and two inputs are given to it. Okay, sorry, I had to make this bubble here. So here I have this NAND gate, and at the output of it, what I will get? I will get A complement B whole complement. Okay, and to get the this complement out from it, I have to again use the inverter here. So the inverter here will be this one given it to this, and here what I will get? I will get A complement B. Okay, so this is the first here. Okay, similarly CD, here I have CD. So the product of CD, let me again use the NAND gate here. So the NAND gate here will be this one. Two inputs are combined. Okay, so first input is given to it while the second one is given to this one, and at the output of it, what I will get? I will get CD whole complement while this is given to another NAND gate. Okay, so this one, these are combined together, and at the output of it, what I will get? I will get CD. Okay, so this is CD. Similarly, here I have A plus B whole complement. So this is clearly the NOR gate. Okay, so A plus B whole complement is the NOR gate. So let me use this NOR gate here. Okay, so let me use it here. This is the NOR gate. Okay, this is the output, and it has two inputs. The first one is the A. Okay, let me use this here, and the second one is B. Okay, so this one is here, and at the output of it, what I will get? A plus B whole complement. Okay, so this is the output of this, and similarly ACD and BE. So here we have what? We can see here that here we have three inputs while here we have two. So let me first use this BE. Okay, so for BE, what I will have to use? I will have to use, this is BE whole complement. So I am going to use the same circuit, which is the NAND gate. Okay, and from it, this is here, and here we will have this B while this E, and from the output of it, I will get BE whole complement, and with it I will have ACD. So for ACD, let me use the gate here, and this is here the 3 input NAND gate, and this is here. Okay, so the first is A here. So let me use this A here with this one. Okay, A, and then the second one is C, and the third one here is this D. Okay, so what I will get here? I will get here ACD whole complement, and in order to remove this complement, what I have to do? This will be here, these two ends will be combined, and here I will get ACD. Okay, we can very clearly see here that this ACD and BE are added together, and to add them, let me use here this NOR gate. Okay, so 2 input NOR gates, and this BE complement and this one are given to it, and it will give me here what? It will give me here BE complement plus ACD and whole complement of it. Okay, so this will be, let me write them more concisely. Okay, so that it is now, so this is now here, and now in order to remove this complement here, what I have to do? I have to use another NAND gate, and the 2 inputs of this NAND gate are combined together. So at the output of it, what I am going to get here? I am going to get here ACD plus BE whole complement, because in this plus or multiplication order doesn't matter. So here the output will be here, and this will be multiplied with this a plus b whole complement. Okay, so the a plus b whole complement is here. Okay, these two has to be multiplied together. So I'm going to use the two NAND gates. Okay, the first one is here, to which this a plus b whole complement is given, to the second one this one is given. Okay, so here what I will get the product of them, and let me write them here. It will be a plus b whole complement with the ACD plus BE complement. Okay, and with that let me use the another gate. Okay, this is here, this is the NAND gate, and it will remove this complement which was here. So okay, so it will remove it, and at the end here what I will get here the let me write it here. Okay, so it will, let me write it here. So it will be AB whole complement, and here ACD plus BE whole complement. Okay, so this is the expression for it. Similarly, all others are here as well. I have, okay, let me write that I have here A prime B. I have the second one which is CD. So it is also here. Okay, CD is also here, while the third one is here, which is composed of these two, and it is here. Okay, so let me bring it back here. Okay, and I have to add these three. Okay, so in order to add them, I am going to use here the NOR gate. Okay, this NOR gate with 3 inputs will give me what? These three will be added together. Okay, it will give me the output, and this output will be the complemented one, because this is the NOR gate. And in order to remove that complement, what I have to do, I have to use another NOR gate with the 2 inputs shorted or combined together, and the output of it will give me this X, which is here. Okay, so this is X, and this one is the output. Okay, which we can very easily compare here. Okay, so this is one of the complex circuits in which we have made the implementation of part A by using the NAND or NOR gates. Okay, so I hope all of these steps would be covered to you guys, and you have grasped the concepts of implementing the logic expression by using the NAND and NOR gates. Okay, so I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. This is section 5.3, and this is related to the universal property of NAND and NOR gates. Okay, so this is question 20 which we are going to solve here in this video, and the statement of this question is that to implement the logic circuit in figure 5.54 using only the NAND gates. Okay, so this is the same figure which we have solved in our previous videos in question number 2. Okay, and I will put the link of it over here so that you can find it for your own understanding. So let me proceed here for question number 20, and here I have written the statement for each of the question and for each of the circuit. So here this is the statement for part A of it, and for part B I have also mentioned the statement for it. Okay, so here let me solve question 20 part A here. So we can very easily see that here we have 3 inputs. So the 3 inputs are A, B, C. Okay, so let me draw them here. So let me first write the inputs here. So this is A, B and C here. Okay, and what I have to do, I have to implement the circuit of it just by using the NAND gate. Okay, so let me first implement each of the term here. So the first term here is A complement, the second term is A complement dot B, the third one is AC. Okay, so let me draw the input lines here. Okay, this is A, this is B, this is C. So let me first get a complement. So to get the a complement, let me draw the NAND gate, okay, so that the two inputs of this NAND gate are combined so that the output of it will be the a complement. Okay, similarly for the second, what I have here a complement dot b. Okay, so to calculate it, what I have to do, I have previously shown you guys that for the AND gate, what would I have first the two input NAND gate, and for after it what I will have another NAND gate which will be connected to it, and the output of it will be the similar to the AND gate. Okay, so to this I have to give a complement and b. Okay, so a will be here, okay, this is b, while a complement is here. Okay, so at the output of it, what I will get here a complement dot b. Okay, so that is the a complement dot b. Similarly for the third one, here I have AC. So for AC I will also use the same combination which I have here, so that would be the first NAND gate, and after it I have to use the same NAND gate to which the two inputs are interconnected, and here I have to apply A and C. So A will be here, okay, this will be A, and C will be here. Okay, so here I will get AC. Okay, so now I have found the values of a complement dot b and AC, and after them what I have to do, let me use them here. This is the a complement, and it is the same sequence with which these are written here. After it I have to use or add them together, because here we can very easily see that this is the addition here. So for adding them together, what I have to do, I have to use the NAND gates. Okay, here I will have the first NAND gate, the second NAND gate, and the third NAND gate. Okay, to them I have to apply what? I have to combine them together. Okay, so I have to combine them together, and after it I have to apply it to the 3 input NAND gate as well. Okay, so the output of them will be given here. Okay, and the output of it will be here. Okay, so now let me apply these here, and I have shown you that by using this combination, what I will have, this will show me the addition or the equivalent of the OR gate when these are represented by using the NAND gates. Okay, so now applying these here and this here, at the output what I will get, at the output I will get x, and this x is equal to the a complement plus a complement dot b plus AC. Okay, so what is this? This is the NAND equivalent of the circuit which is given in part A, and the same is given previously by using the other gates. Okay, these are the other gates, while this implementation basically shows me the implementation of the same logic circuit by using the NAND gates. Okay, so that is for the part A, and in our next video we will try to compute the same for part B. Okay, till then take care of yourself, and I will see you soon. Welcome back guys, and this is section 5.3. previously we solved the part A of this question number 20, and we have shown you guys that how to implement or represent any logic expression by using the NAND gates because of the universal property of the NAND gate. Today we are going to solve this part B, and here we can see that how many inputs do I have. So the number of inputs we have are A, B, C, D, 4. So let me first write them here. So let me start writing them here. So A, B, C, D, and this is part B. Okay, let me mention it here as well, and after it, let me draw the input lines. So this is 1, 2, 3 4 or A B C D. What I have to do, I am going to solve it by using the same method which I have previously done. So this is A complement dot B and this is A complement CD. So I have to complement A first. So let me complement this first A by using the NAND gate, and the two inputs are combined together. This is given here, and at the output of it I will get A complement. Okay, the first product here is A dot B. So let me use the same product here and the same thing here, and that is the two NAND gates. Okay, the first one is here while the second one is the inverter, which is like this one. Okay, I have told you that all of this is basically the example of the AND gate, which I have previously explained in a separate video. Okay, so after it, what I have to do, I have to basically give the inputs to them as the what this is A complement and the second one here is B. So the output of it will be A complement dot B. Okay, the second product is A complement CD. So for it I have to use the 3 input NAND gate. Okay, so 1 2 3, and this output is again given to another NAND gate for the inversion purposes, and therefore the 3 inputs to it are, this is A complement, the second one is the C, the third one here is D. So the output of it will be what? A complement C D. Okay, so this is the, so what is this these are basically the two products which I have to add and then take the complement of them. So again using the same adder, because this is the addition, so using the same adder by using this NAND gate. This is the first NAND gate, this is the second NAND gate. The two inputs are basically combined together, and these inputs are given to them. Okay, and at the output of it, these are now given to the inverter. Okay, so now here these are now given to this NAND gate. Okay, so here what I will get, the output of it will be what? That would be A complement dot B plus A complement CD. Okay, so as here we have these whole complement as well, so therefore I have to use another inverter here as well. So this will invert it, and at the output of it, what I will get? I will get A complement dot B plus A complement CD, and this is what? This is the answer of part B here, in which I have implemented the overall circuit which was mentioned here by using the NAND circuit, and that is here. Okay, so that is the solution for part B with us, in which we have seen that, sorry, this is the whole complement here as well. Sorry, I have made a mistake. So the whole complement here as well, because of this NAND gate as well. So this is the solution for part B, in which I have explained and showed all the steps which are used for converting any of the logic circuits into the form in which NAND gates are used. Okay, so that's it for today, in which I have solved question 20, and I will solve more questions like this in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So this is section 5.3, and today we are going to solve question 21 of it. So the statement is the implementation of a logic circuit in figure 5.58. Okay, so this is the figure 5.58 using only NAND gates. Okay, so previously we have seen that we can implement the plenty of the fundamental circuits by using the NAND gates. Okay, here we are given a NAND gate, and here we have to implement it by using the NAND gates. Okay, so this is a fundamental circuit, logical circuit, and we have to implement it by using the NAND gates. Okay, so what will be the strategy here? Okay, so first of all, what we have to do initially, we will have the logic circuit. Okay, from this logic circuit, what we have to do, we have to find the logic expression, okay, and from this logic expression we will have to implement it by using the NAND gate. Okay, so it would be our strategy here. Okay, so let me first find the logic expression from it. So this is the logic circuit which I have, and from it let me find the logic expression. Okay, so to find the logic expression, let me use this color. So here we have the first gate, so this is a NAND gate here. So in order to find the output of it, it will be A, B whole complement here at this point, and here we will have what these two inputs B and C are applied here, and here we have a NOR gate here. So B plus C whole complement will be the output here. Okay, so here to this gate both of these are applied, and at the output of it, what we will get here, we will get AB complement dot B plus C whole complement and the whole complement of it as well. Okay, so this is the output of this circuit. Similarly, this is now applied here, okay, to this NOR gate, and to this C is also applied. So here what we will get to the output of it, this will be X, and here we will get A B whole complement, okay, dot B plus C whole complement and the complement here as well. Okay, and also the C here, with which I have to use this whole complement as well, and this is because of what, this is because of this NOR gate. Okay, so we can also simplify it by using the DeMorgan's law. Okay, so let me use the DeMorgan's law here as well in order to simplify it. So according to the DeMorgan's law, these two will be separated out. Okay, so what will happen, we will get AB complement dot B plus C whole complement, and the complement of it is here, while here it will be C complement, while the sign you can see that has been changed to multiplication, while this complement has been divided over both of them. Okay, so this is the, let me use another. Okay, so this is another complement here. So these two complements, let me use this red color, these two complements will cancel each other, and here what we will get at the output of it, here we will get AB whole complement dot B plus C complement dot C complement. Okay, or we can also write it like A B C complement dot B plus C whole complement. Okay, so this is the answer of this circuit, that we have the logic expression, and this logic expression has been given in the form which is given here. Okay, so now what we have to do, we have to implement it by using the NAND gate. Okay, so we have a logic expression here, and now we have to implement it by using the NAND gate. Okay, so let me move down somehow. Okay, so now let me move down. So here let me see that how many inputs do I have. So I can see that I have A, B, C, 3 inputs. So let me use them here, A, B, C. Okay, so the 3 inputs are 1, 2, 3. Okay, so as I have to use the NAND gate, so therefore I have to implement this one first. Okay, so this one first, then this one first, and I have to multiply them together by using this sign. So here first of all, this circuit will be what, in order to implement it, what I have to do, I have to use the NAND gate. Okay, so NAND gate is here, and here the 3 input NAND gate should be used. So here this first, this second, while this third, and here we will get what, A, B, C whole complement. Okay, after it, what I have to do, I have to find the B plus C whole complement, and in order to find this NOR gate from this NAND gates, what I have to do, I have to use the two NAND gates. Okay, the two inputs NOR gates in which the two inputs are combined together. Okay, and here then these two are given to another NAND gate. Okay, here this is another NAND gate, and it will give me what? It will give me the output, which will be the OR gate. So in order to take the NOR gate out of it, what I will do, I will apply it to another NAND gate as well with the two inputs combined together. Okay, so here we have B plus C, so let me use this B here and C here, and at the output of it, what I will get here B plus C whole complement. Okay, so these are the two inputs which we have here, and these are, okay, we can see that this is 1, this is 2, and these now have to be multiplied together by using this multiplication sign, and for it I can use this NAND gate. Okay, two input NAND gates. So first here the input is here, the second one is here, while at the output of it, what I will get here the ABC whole complement dot B plus C whole complement with the whole complement over it. Okay, so in order to remove this whole complement, what I have to do, I have to use another NAND gate to which this input is applied, and at the output of it, what I will get, this complement will be removed because this is an inverter, and at the output of it, what I will get ABC whole complement dot B plus C whole complement as well. So this is the output, and therefore this is the output which we have found from here, and this is the circuit which is basically the implementation of the logic expression by using the NAND gates. Okay, we can see that here we have these NAND gates, and these are the important gates which we have implemented here. Okay, so that's enough for today, and which we have seen the fundamental steps of converting any logic circuit to their NAND gates counterpart. So in the next question we will talk about some other questions in which we will have to implement the same circuit by using the NOR gates. Okay, so the steps will remain the same because we have found the logic circuit or logic expression from this logic circuit, and then the only step will remain there would be the implementation of it by using the NOR gate. Okay, so I think it's enough for today, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So in previous question we have seen the implementation of figure 5.58 by using the NAND gates. Okay, so this is question 23, and we have to repeat the same problem using only NOR gates. Okay, so previously we have seen that the logic expression for our circuit is x equal to a b c whole complement dot b plus c whole complement. Okay, so previously we have mentioned some steps. So if we have a logic diagram here, so we have a logic circuit first. So from this logic circuit, what we will have to do, we will have to find the logic expression. Okay, and from this logic expression, what we have to do, then we have to implement them by using the NAND NOR gates. Okay, so here we have to use the NOR gate because here we are told that we have to implement it by using the NOR gates. Okay, so again the same strategy we are going to follow. How many inputs do I have here? So I have here 3 inputs, and here I'm going to use the blue color for them. So here I have A, B, C, 3 inputs and the input lines are these 3. Okay, and after it, what we have to do, first of all, I have to implement this one, then this one, and at the end I have to multiply them together. So initially ABC is the word, this is the NAND of it. So here what I have to do, I have to use only the NOR gate. So in order to use the NOR of it, first of all, let me use the 2 input NOR gate here. Okay, so here this is a 2 input NOR gate for the first one. Secondly, the second NOR gate, okay, with the 2 inputs combined together, and these third NOR gate with the 2 inputs combined together. Okay, so these are then given to the another NOR gate, okay, which has 3 inputs. Okay, so this will be connected here, this will be here, and it will be here as well. So at the output of it, I will get the AND of it, so it will be given to another gate. Okay, so let me use another NOR gate here, with which the 2 inputs are combined together, and this is given to it, and the output of it, I will get the NOR output. Okay, so it has the 3 inputs, and let me give these 3 inputs to it. Okay, so this is the third input, and we can very easily see that this gate, okay, let me point it out, that why have I drawn it first, because this is a gate which is the implementation of the NAND gate. Okay, for 3 input NAND gates. Okay, so this is a NAND gate. Here we have, so at the output of it, what will we get? We will get here A, B, C whole complement. Okay, the second thing we have here is the B plus C whole complement. So this is a very straightforward operation here, and this is the NOR operation. So let me use this NOR gate here. This is a NOR gate. Okay, to this we have 2 inputs, to them let me apply this first B, and then to the second one let me apply this one, and at the output of it, what I will get? I will get B plus C whole complement. Okay, so this will be the output what we will get here. Okay, so these are the 2 outputs. So the first one is A, B, C whole complement, the second one is B plus C whole complement. The final operation here is to multiply them together, and we have seen that we have already deployed the AND gate by using these circuits. Okay, so what is this? This is the AND gate. Okay, so this is the AND gate. Let me take it and apply it here. So let me apply it here, as we have 2 inputs. So the 2 NOR gates here would be this 2 inputs, and this is combined together, while this one is another NOR gate with this 2 inputs, and these are combined as well. This is given to it, while this is here, and at the final stage of it, this is, so the 2 inputs, okay, these are applied, and the output of it will be what? This will be the multiplication of both of these terms. So at the output of it, what I will get? I will get A, B, C whole complement dot B plus C whole complement, which are basically the inputs to this gate, and this is the final stage of this circuit building, in which we have seen that we have developed a circuit by using the NOR gates. Okay, so this is the implementation of the same circuitry by using the NOR gates, and I hope you have understood all the steps which are involved in developing the logic circuit by using the NOR gates. Okay, so I think it's enough for today, and I will see you with some more interesting questions in our upcoming video. Take care of yourself, practice over all this stuff, and I will see you with more interesting questions in our upcoming video. Thank you so much. Welcome back, guys. So this is question 24 in section 5.4, and in previous questions you have seen that we have been implementing the logic expressions by using the NAND or NOR gates. Okay, so this is one of the same parts of our questions, and here we have to show that how the following expressions can be implemented as stated using the NOR gates. Okay, so we have to implement all of these parts by using the NOR gates. Okay, so let me first start the part A. So in A we have x equal to ABC. Okay, so what is here, we have the three inputs which are ANDed together. Okay, so the first thing is we have three inputs, so let us have A, B, C, three inputs. Okay, so we have these three inputs, and what we have to do, we have to implement this logic expression by using the NOR gate. Okay, so the AND operation in NOR gates can be implemented by the NOR gate. Let me draw it by these three NOR gates. Okay, we have three NOR gates because three inputs, and this one as well. Okay, so we have these three NOR gates, and the inputs of these NOR gates are combined together. Okay, and after it, these are given to another NOR gate, which is the three input NOR gate, because we have to connect these three outputs from these three gates to it. Okay, so it will be what, it will be the output, and it will be like, let me represent it. So it is what, it is just like a AND gate. Okay, so this is what, this is the AND gate composed of all the NOR gates. Okay, so let me connect these inputs to it. So this is the first input, this is second, while this is the third input, and at the output of it we will get x, and this x is A, B, C. Okay, so this is the NOR gate representation of part A. Similarly, in part B, what do we have? In part B, let me write that we have x equal to ABC whole complement. So what do we have to do? We have to implement the same AND gate here. So again we would have ABC, and these are the input lines. Okay, so we have to implement the same AND gate here. Okay, so when this will be implemented, so let me implement it here in this diagram. Okay, so after it, when we will get here, what we will get here at the output of it, x equal to ABC. Okay, so at the output of it we will represent or write the inverter here, and it will be what, the output of it will be x equal to ABC whole complement. Okay, so let me draw all these gates here. So again we would have three NOR gates. Okay, this is first, second, and third NOR gate. Okay, the inputs of them are combined together, and these are the gates, and these inputs or the outputs of these three gates are given to the three input NOR gate. This is connected to it, and it is here, and this one is here, while these are connected to them. Okay, so this is the solution of part B, which is here. Okay, similarly, now I have to implement the third part of it, and that is part C. So in part C we are given that we have to implement x equal to A plus B. Okay, so how many inputs do we have? We have two inputs, and these are A and B. Okay, these two inputs are given to a NOR gate. Okay, so at the output of this NOR gate, what would we get? We would get A plus B whole complement. Okay, so what do we have to do? We have to remove this whole complement. So therefore I am going to deploy another NOR gate. The two inputs of this NOR gate are connected, so it will serve as an inverter. Okay, so when this input is given to it, at the output of it we will get A plus B whole complement, so it will be removed, and so at the output of it the complement will cancel out the whole complement, so therefore I will get here a plus b. Okay, so this is the solution of part C here. Okay, so we have solved 3 parts of this question, and I hope these are understandable, and in our next part we will try to solve D, E, F and G. So I think it's enough for today, and I will see you with some more interesting question and some more interesting part of this question in our upcoming video. Till then, take care of yourself. Welcome back, guys. So previously we have solved first 3 parts of question 24. Today we are going to solve part D, E, F and G. Okay, so let me start part D here. So in part D, the expression is A plus B plus C complement. Okay, so how many inputs do we have? We have A, B, C, 3 inputs, and these are the input lines. Okay, we have to see that we have to add them together, so therefore A will remain is in its original form, B will be in its original form, while C has to be complemented. Okay, so therefore I have to use here the NOR inverter. Okay, so the two inputs of it are combined together, so therefore here I will get this C complement, this will be B and this will be A. Okay, so now this is given to the 3 input NOR gate. Okay, so this is a 3 input NOR gate, so let me give these inputs to it, and at the output of it what I will get A plus B plus C complement and the whole complement of it. Okay, so in order to remove this complement, this output should be applied to another NOR inverter, so therefore the NOR inverter here we will have would be this one, the 2 input NOR inverter, and it is given to it, and therefore at the output of it what would we get? We would get A plus B plus C complement. Okay, so the complement applied by this final NOR inverter will cancel out the available complement. Okay, similarly in part E of our question, this is the solution of part D. In part E of our question, the we have here is x equal to AB whole complement plus CD whole complement. Okay, so what will be the procedure here? First of all, we have to see that how many inputs do we have. So here we have 4 inputs. Okay, so let me use them here. So this is part E, and here the inputs are A, B, C, D. Okay, so we have these inputs, and the input lines here are 1, 2, 3, 4. Okay, so let me first use them in such a way that initially this term will be found out, and then this one, at the end we have to add them together, and all of these operations will be carried out by the NOR gate. Okay, so let me first draw 2 NAND gates. Okay, so the 2 NAND gates here would be, this is the first, this is the second NOR gate. Okay, the 2 inputs of it are combined together. Okay, and these are given to this one. Okay, so the 2 inputs here, so let me apply it here, and the output of it, this will be the AND gate. Okay, we can see that this is the AND gate, and in order to invert the output of it, we have to implement it to another NOR gate as well. So here it will be, okay, so at the output of it we will get what? We will get, if the 2 inputs are applied here, the output of it will be AB whole complement. Okay, similar gate can also be applied here. So here this is the first NOR gate with the 2 inputs combined together. Here the second NOR gate, the 2 inputs shorted together. Okay, the third NOR gate with 2 inputs, these 2 inputs are applied to it, and it will give me what? This is the AND gate. Okay, so in order to invert the output of this AND gate and to make it the NAND gate, we have to use another NOR inverter. Okay, so let me apply this input here, this here, so at the output of it we will get what? CD whole complement. Okay, so these are the terms we have found out. So we have found out AB whole complement, we have found out CD whole complement. Now we have to add them, and in order to apply the OR gates, what do we have to do? We have to use the NOR gate, which is followed by another NOR gate, and it will work as the inverter. So at the output of it we will get what? The addition of both of them. So let me apply it here and it here. So at the output of it, what would we get? We would get AB whole complement plus CD whole complement. Okay, so that is the output. Okay, and here we can very easily see that, let me use this color, that this is the first AND gate which we have applied here. This is the second AND gate, okay, which we have applied, and these two are for the NAND operation, while we can very easily see that this is what? This is the OR gate. Okay, so this is the OR gate, and these two are the, and this one as well. So this is the AND gate, and this is also the AND gate. Okay, so this is the solution of part E here. Okay, similarly after it we have to implement part F. So I will see you in our upcoming video in which we will implement this part F of it. So till then, take care of yourself, and I will see you soon. Welcome back, guys. So today we will solve the remaining parts of our question 24, and this is section 5.4. okay, so the remaining parts here are F and G. Okay, so let me start part F here. So according to the part F, the output or the logic expression we have is A plus B multiplied by C plus D. Okay, so what will be the operations here? Let me first demonstrate them. First of all, we have to add A plus B, and then we have to add C plus D, and then at the end we have to multiply them together. We know from our previous videos that how to implement the OR gates and AND gates by using the NOR gates. Okay, so that is also the objective of this question, that we have to implement this logic expression by using the NOR gate. Okay, so first of all, let me see that how many inputs do I have. So I have 4 inputs, and these inputs are A, B, C, D. Okay, so the input lines are 1, 2, 3, 4. Okay, so let me first add A plus B. So the adder here is this NOR gate, which is followed by another NOR gate for the inversion purposes. Okay, so the two inputs of it are combined together, and the output of the first gate is given to it. Okay, so when this first input is given to it, what will be the output of it? It will give me A plus B. Okay, so why is this? Because this is the implementation of the OR gate, okay, by using the NOR gate. Similarly, the same gate can also be used here. So here we would have the first NOR gate, 2 inputs are given to it, the output of it, which are now given to what? The NOR inverter, and the output of it, what would we get? C plus D. Okay, so we have found out our two operators, we have found out our two outputs, and these have to be multiplied together because here the two have to be multiplied. Okay, so the AND gate here, as we have previously seen that by using the NOR gate, AND gate implementation will be like, so this is the first AND NOR gate, this is the second NOR gate, the two inputs are combined together, here the two inputs are also combined together, and these are given to the final 2 input NOR gate. Okay, so let me give it to it, this one here. So here we have this NOR gate, and we can very easily see that this is the implementation of what? This is the implementation of the AND gate. Okay, so let me apply my inputs here. So this will be the first input. Let me So the first input here will be this one, the second will be this one, and at the output of it, what I will get a plus b multiplied by c plus d. So that is the output of my question, and we have seen that these are implemented by using the NOR gates, which are implemented here as well. Okay, so that is the solution of part F. Similarly, for part G, let me see that how many inputs do I have, which is the first step here. So in part F, part G, we have x equal to a, b, c and d, e whole complement plus a, b whole complement plus b, c, e whole complement. Okay, so we have to implement it by using the same NOR circuitry, and we have seen from our previous question that we know all the we know that how basic circuits like AND, OR and NOT can be represented by using the NOR gates. So therefore it is not very difficult for you to implement this one. So therefore this is your task to carry it out. So let me give you some hints at how to do it. So let me use this yellow color. So this is the word, this is the AND operation. Okay, and here this will be the NAND operation of 3 inputs. Okay, and here we can see that and okay, and with this OR operation. Similarly here this OR as well. Okay, and this is the AND operation here, and when this all is calculated, this will be ANDed together with it as well. Okay, so this is the solution of part G, and I strongly recommend that you guys implement this expression by yourself because I'm not going to do it. Previously I have solved all the relevant examples just like this one, and in our upcoming video we will talk about the implementation of the same gates by using the NAND gates. So till then, take care of yourself and I will see you soon. Welcome back guys. So this is question 25. Okay, and we have to repeat the problem 24 by using the only NAND gates. Okay, so in question 24, what did we do? We have implemented all the logic expressions which are stated here by using the NOR gates. So here we are asked to do the same by using only the NAND gates. Okay, so let me repeat part A here, and we will follow the same procedure what we have done for our question 24. So the first question we have is ABC. Okay, so this is ABC, and we can see that this is the AND operation which has been carried out in between the 3 inputs. So we have 3 inputs A, B, C. The 3 inputs are 1, 2, 3. Okay, so these 3 are given to a 3 input NAND gate. This is a NAND gate. Okay, so at the input of it we will have these 3, so output of it will give me A, B, C whole complement. Okay, so what do we have to do? I have to remove this complement, so therefore the complement of it will be cancelled out by using the NAND inverter, because it will complement the complemented term and the output of it will be the uncomplemented overall term. Okay, so let me use the NAND gate here as well. So this is the NAND gate with the 2 inputs combined together. This is the NAND inverter, this is connected here, and at the output of it, what would we get? We would get x equal to ABC. So this is what, this is the implementation of the x equal to ABC, and this is a simple AND gate which can be implemented by using the NAND gates. Okay, similarly in part B we have x equal to ABC whole complement. So this is what, this is the NAND operation which has to be carried out. So therefore the 3 inputs we have A, B, C, these are the input lines, okay, which has to be given to a simple NAND gate. Okay, the 3 input NAND gate, so these are applied here, 1, 2 and 3. So at the output of it, what would we get? We would get a, b, c whole complement. Okay, so these are what? These are the outputs. So this is the output of the first gate, this is the output of the second gate, and similarly we can very easily see here that this one up to here, this is the implementation of the what? AND gate by using the NAND gates. Okay, similarly part C here is what? So let me see part C here. So the part C here is, this is part C. So we have here x equal to a plus b. So we have two inputs which are a, b. So the input lines are here, and we have to add them together by using the OR gate, but we have to implement it by using the NAND gates. Okay, so therefore the OR gate implementation by using the NAND gate is here. So let me first draw two NAND gates. Okay, this is a NAND gate, this is a second NAND gate. The output of them are given to another NAND gate. Okay, so here this is the NAND gate with two inputs, and these are given here as well. So what is this? This is for the two input. This is what? This is the OR gate for the two inputs. Okay, so let me combine them here. So the inputs are applied here, and at the output of it, what would I get? I will get a plus b, and that is what? That is the answer of my question. Okay, so of part E here. Similarly, if I want to implement part D, I will show you in our upcoming video that how to implement part D. So till then, take care of yourself, and I will see you with some more interesting questions in our upcoming video. See you soon. Welcome back, guys. So this is question 25, and in previous video we have seen that we have implemented part A, part B, part C by using the NAND gate. So today we are going to talk about the remaining parts. So the part D here is D is x equal to A plus B plus C complement, and we know in our previous video that how to implement the OR gate by using the NAND gate. So let me first see that how many inputs do I have. So I have three inputs, so let me apply the three inputs. So A, B, C, this is the first, second, third. Okay, the C has to be complemented by using the NAND gate. So therefore let me first draw here the NAND inverter. So the two input of it are combined. So here I will get C complement, and from here these are the inputs. Okay, so A, B, C complement I have to add them together by using the OR gate. So the OR gate implementation by using the NOR gate is here. So this is the first NAND gate, this is the second NAND gate. Okay, the third NAND gate is here. Okay, the three NAND gates are here, and we have to short the two inputs. Okay, so here we have these NAND gates which are combined by a 3 input NAND gate here as well. So what is this? This is the OR gate, and let me draw them. So this is what? This is a box in which we have the NAND implementation of a 3 input OR gate. Okay, so let me apply these inputs to it. So the first input is here, the second one is here, while the third one is here, and at the output of it we will get the summation of the inputs, so which are x equal to A plus B plus C complement. Okay, so this is what? This is the summation of the 3 inputs. Similarly, we can see that this is the solution of part D here. Okay, so for part E, what do we have to do? So in part E we have x equal to AB whole complement plus CD whole complement. Okay, so we have this expression and we have to implement it by using the NAND gate. So the 4 inputs, because we have here A, B, C, D, so the 4 inputs are A, B, C and D, and the input lines are here. Okay, so what do we have to do? First of all, we have to implement AB whole complement, then CD whole complement, and that is the NAND gate implementation. So the two NAND gates, okay, this first, second NAND gates, which are added together by this OR gate. Okay, so let me proceed here. So the first NAND gate is here, 2 input NAND gate. So the first input is applied here, the second is here, and at the output of it I will get AB whole complement, and at the second NAND gate will be here the 2 inputs, and the first one is applied here, second one here, and at the output of it we will get CD whole complement, or let me draw them correctly. So CD whole complement. After we have to add them together, and the adder by using the NAND gate is this one, the second one. Okay, the two inputs are combined together and these are applied to the final 2 input NAND gate. So these are applied here, and this is what, this is the input. So when these two are applied here, at the output of it, what would I get? I would get AB whole complement plus CD whole complement, and that is what? That is X. Okay, so this is the solution of it. Okay, where we have implemented our gates, in which this one is what? This is the NAND gate implementation of the 2 input OR gate. Okay, so while these are the NAND operations. Okay, so this is the solution of part E by using the NAND gates, and I hope all the steps which has been carried out here are now understandable, and I will see you with some more interesting questions and some other parts of this question in our upcoming video. Take care of yourself, and I will see you soon. Welcome back, guys. So today we are going to solve the remaining parts of question number 25, in which we have to implement the expressions by using the NAND gate. So the part F of our question is, so this is part F, and in part F we have A plus B multiplied by C plus D. Okay, so these are the operations which we have to carry it out. So the first operation is this OR operation. The second one is also the OR operation, while at the end these has to be ANDed together. Okay, so we have to carry it out. So let me first denote my inputs. So these are A, B, C, D. Okay, so initially I have to implement the 2 OR gates by using the NAND gate. So the first NAND gate is here. This is the first NAND gate. The second NAND gate is here. Okay, so the 2 inputs are what? These are combined together, while these are applied to the 2 input NAND gate as well. Okay, so this is what? This is the first OR gate, and the input lines are here. Okay, the first input is given to it, the second is to it, and at the output of it I will get what? I will get A plus B. Similarly, the same gates are drawn here. Okay, this first one, the second one. Okay, so here we have, okay, and this output, while this is connected to this one, and here C is applied here, D is here, and here we will have this C plus D. Okay, we can very easily see that this is a first OR gate, this is a second OR gate, and these are the 2 OR gates representation with the help of the NAND gates. Okay, so the two A plus B and C plus D, two inputs are obtained from these combinations. Now we have to apply the AND gate here. So the AND gate here will be, let me first apply here the NAND gate. Okay, the two input NAND gate. This NAND gate, and at the output of it we will get the complemented version, which has to be removed by using the NAND inverter. Okay, so this is the NAND inverter and the two inputs will be applied. So at the output of it, what would I get? I would get A plus B multiplied by C plus D. Okay, so that is the solution of my question, and here we have seen that this is the implementation of what? This is the implementation of the AND gate by using the two input NAND gates. Okay, this is the solution of part F, and similarly I encourage you guys to implement the part G of this question by using the same concepts which we have deployed so far. So I think it's enough for today, and I will see you with some more questions in our upcoming video. Till then, take care of yourself. Hello guys, I hope all of you will be fine. So again, this is section 5.5 and we were talking about the pulse waveform operations. Okay, so this is question number 28, which has been employing the concept of the pulse waveform operations. And what do we have to do? The output of the logic circuit and input waveform in figure 5.59 is passed through an inverter. Okay, so this is basically the inverter and it has been passing through this circuitry. Okay, so what do we have to do? We have to draw the output waveform. Okay, so this is a waveform of the inputs, and again, what do we have to do? Again, we have to slice them according to their changing edges. So the first edge is here, the second one is here, because now this second waveform has been changing its level. The third one is here. Okay, fourth one is here, fifth one here, this is the sixth one, and so on. Okay, so after finding all the edges here and all the instances where any of the input levels has been changed, we have to find that instances. Okay, so prior to this, what do we have to find out? We have to find out the output of this circuit. So therefore it is mandatory that we should find the expression for it. Okay, so what should be the expression? So let me use it here. So here what would be the output? It will be, we can see that A is applied, B is applied, A is complemented by using this bubble here, B is complemented by this bubble, and this is now passed through this OR circuit. So here we will have A complement plus B complement. Okay, so now this A complement plus B complement and this B, okay, this is here B, these two are applied to this second NOR gate, and here at the output of it, what would we get? We would get A complement plus B complement. Okay, this is the first input, then OR of the second, and then as this is a NOR operation, so here it will be complemented. Okay, so we can see that here what input do we have here? So here we have two inputs A and B and the two output and a single output, which is A complement plus B complement plus B and whole complement. So let me write it here. So it is A complement plus B complement plus B and the whole complement of it. Okay, so this is the same expression and this is X. So now let me use the DeMorgan's law. So applying DeMorgan's law here, what would we get? We know that according to the DeMorgan's law, if we have this expression A plus B whole complement, so it will be the complement of the first term, complement of the second term, and the operation here will be inverted. If this is the addition, it will be multiplication here, and vice versa. Okay, so here applying the same concept, what will we get? We would get A complement complement. Similarly, the second entry here, and that is b complement and the complement of it, and the third entry here which is only b, so complement of it, and we can see that here these are the addition, so therefore it will be the multiplication here. Okay, by seeing it here we can see that this is the complement of a complement here, complement of a complement, and complement basically cancel the effect of the other complement, so therefore the complement of a complement is basically no complement, so here we will get a dot b complement. Okay, so this is what this is x, or we can see that this is the expression which is applied here. Okay, but here in order to see the output of it, we can see here very easily that this is b dot b complement, and according to the Boolean algebra we know that x dot x complement is always equal to 0. Okay, so using it here, what I will get a dot 0 which will ultimately give me 0, and that is the value of x here. Okay, so this is the output, and we know that prior to the application of the any inputs, we can see that whatever the inputs are, the output here will be equal to what? That would be equal to 0. Okay, so let me use it here, and we will see that if this is a level, so output of it will always remain what? It will always remain 0 here. Okay, because this is a 0, so that is what this is the waveform for x. Okay, so I think you have grasped the concept that how can we find out the output of any gate if different pulses are applied here. And in previous question which was basically the question 29, we have discussed the same thing, because there we had some logic expression, and first we found out some logic expression of a circuit, and then we had applied the inputs which were in the form of a and b. Okay, so I think it's enough for today, and I will see you with some more interesting stuff in our upcoming video. Take care of yourself, and I will see you soon. Welcome back guys, I hope you will be fine. So this is section 5.5, which is the pulse waveform operations in our digital logic circuits, and this is question 29 which we have to solve. So for the logic circuit in figure 5.60, okay, so this is the logic circuit. Draw the output waveform in the proper relationship to the inputs. Okay, so these are the input waveforms which we have here, and this is the logic circuit. Okay, so in this circuit we can very easily see that we have two waveforms. So let me first introduce them. What are those waveforms? So here we can see that in A we have a certain value which is at the bottom, and then it releases and goes upward, and after some times it get back to the lower bottom, and then it goes up to a certain other level. Okay, so what are these values? So this is what this value is, basically the 0 value, and this is 1 value. Okay, similarly this is the 0th level, and this is 1 level. Okay, so in order to draw it, let me draw it here as well on the x and y axis, and we can see very clearly here that this is 1 and this is what? This is 0. Okay, so these are the waveforms which alternatively get the values which are either zeros and ones, and on the basis of them we have to find the output of them. Similarly in our input B, we can see that there are also the same levels which are somehow faster than the input A we have, and on the basis of it we have to find the output of the circuit which we have here. Okay, so this in the circuit, what is the logical expression for it? So here we can see that this is B which is applied here, and here we have got B complement. Okay, so this is what this is the output of this circuit, and here this A is applied here because of this bubble. It will also be the A complement. Okay, and this B complement will be removed by this bubble as well, so it will also be the what? This will be B. So here let me call it Y. So at the Y, what I will get here, I will get A complement dot B. Okay, so we can see that here this A is complemented by this bubble, while this B complement bubble is removed by this another bubble. Okay, so this is Y. So this is A prime dot B. So we can find this Y here as well. So the Y output will be what? This is a complement dot b. Okay, so this is a complement dot b. So let me find out the value for it. So let me represent it by using this color. So we can see that we have different levels for it. So we have first this level, then this level, okay, then we have this level, okay, this alternation, this, okay, this up to this it is constant, and this one, this one, this one, and the last one is here. Okay, so what are these? So let me see them. So writing them here, here we can see that at this first level the value of a is 0 and the value of b is 1. Okay, so when the value of up to this, the value of a and b both are zeros. Okay, we can see them here, these both are zeros. Similarly, at this value we can see that here the value of a is 1 and the value of b is 0. Okay, here both values are 1 1. Here the value of a is 1 while the value of b is 0. Okay, here both values are zeros. Here one is 0, the other one is 1. This is 0, the other one is 0. Here first one is 1, the other one is 0. These two are 1 1. This is 1, this is 0, while here we can see that both of them are zeros. Okay, so on the basis of the waveform alternations we have found out their values. Okay, so let me draw the diagram for it. So when the two are 0, so we can see that here the output will also be 0, which can be mentioned here. So let me draw it by using this one. So here we will see that it will also be 0. Okay, so here it will be 0 when one which is a is 0 while one, b is 1. So 0 complement multiplied by b1, that would be 1. So here we will have what? Up to this point we will have 1. Okay, here a is complemented, which will be 0, and b is what? We can see that b is now 0. So 0 multiplied by 0 is 0. So here we will have 0 up to this point. Here we can see that both are 1 1 while a can be complemented and it will become 0. So therefore it will remain 0 here as well. Here in this part we can see that a is 1, which will be complemented and give me what? Give me 0. So 0 multiplied by 0 will also be 0. So it will remain 0. Okay, here we can see that b is 0 while this will become 1. So 0 multiplied by 1 will be 0. So it will remain here. Similarly, now we can see that here b is 1 while a is 0. So complement is a is 1. So 1 1 is 1. So therefore here we will get 1. Okay, here both of them are 0. So it will give me 0 because if a is complemented, b will remain 0 and it will make this product equal to 0. Okay, here we can see that a is 1 while b is 0. So this b is 0. So therefore it will remain 0 here as well. Okay, here two are 1 1. So we can see that a will be complemented and give me 0 and their product will remain 0 here as well. Okay, here a is 1 while b is 0. So b is 0, any one of them is 0, it will give me 0. So here I will get 0 as well. Here both of them are 0. So here this will be the waveform for this a prime dot b. Okay, so this is what? This is for the y. Okay, after it what I have to find out? I have to find out the value of x. So let me find out the value of x, and it will be the product of this b which is coming from here and this a prime dot b and the whole complement of them, because these are NAND together. So we can see that a complement dot b and these are multiplied with b and this is the whole complement. So this is what? This is x. So let me find out the value of x here as well. So it will be x, and in order to find it out, the value of it is what? A prime dot b multiplied by b and the complement of them. Okay, so a prime dot b is already calculated. Let me find out what we have to find out. A prime dot b multiplied by b. So let me first find the what a prime dot b multiplied by b. Okay, so let me find it out. So as the both of them are multiplied together, so let me extend it as well. Okay, let me extend it. And here as well. Okay, so if any one of them is 0, it will be 0. So in first instance b is 0 and this is 0, so it will remain 0 here as well. So let me use this color, so it will be 0. Okay, in the second instance both are 1, so it will be 1. In the third instance b is 0, so therefore it will remain 0. In all of these instances it will remain 0 because the level of it is also 0, so the product will remain 0. Here we can see that both of them are 1, so here it will remain 1. Here all of them are 0, so it will remain 0 here as well. Okay, so this is what, this is the value of it, and at the end we have to find out the value of x, and x is what, that is a complement dot b multiplied by b, and the whole complement of it means the overall complement of it, and this will be the opposite of it. So it will be 1, it will be 0, it will be 1 here. Okay, here it will be 0, it will be 1 here. Okay, so this is what, this is the waveform which I wanted to find out, and this is the required waveform which we wanted to have, and this is what, this is the answer of my question. Okay, so I hope all the steps are now understandable to you guys, and you can find out the output of any waveforms or pulse waveforms which are given as input to any logic circuit, because this is what which has been performed in the real world operation. So I think the concept is now clear, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back guys, this is again section 5.5 and this is question 30. What do we have to find out? So here the statement is, for the input waveform in figure 5.61, what logic circuit will generate the output waveform as shown? Okay, so what is the output waveform? So the output waveform is here, this is what, this is the output waveform x, and these are the inputs which we have. So the inputs we have are a, b and c. Okay, so we have to find out the what, we have to find out the logic circuit for it. So for it we have different steps. Let me write down one by one. So what will be the step? So we have to identify the inputs or binary value of the inputs for which output is equal to 1. Okay, so this will be what, this will be the step number 1. So we have to identify the inputs for which the output is 1. So let me first identify them. So here we can see that this is 1, this is 1, this is output. Okay, we can see that x is the output. Here this is also 1, 1, 1, 1. Okay, so for these level I have to find out the inputs or the binary values of the input. So for the first one I can see that the combination I have here is the 1, 1, 1. For the second I have this 1, 0, 0. Okay, so this is the combination. For the third one, this is again 1. I can see that for it I have 1, 0, 0. For this one, this fourth one I will have 1, 1, 1. Okay, for this one I will have 1, 0, 0, and for the last one here I will have 1, 0, 1. Okay, so these are some combinations for which I have got these values. Okay, so after it, after finding them, what do we have to do? So let me first write them, what are the combinations. So the second step here will be to write binary values or identified binary values in the form of a truth table. Okay, so whatever we have found out, let me write them in the form of a truth table. So we have A, we have B, we have C, and we have here X, okay, which is the output. So what are the combinations which we have obtained? So this is 1 1 1, this is the first one. Here for it I have output equal to 1. Okay, the second combination is here, that is 1 0 0 1 0 0, so the output for it is 1. Okay, this third one is the replication of the second one. This fourth one is also the replication of the first one. Okay, this is also the replication of the second and the third one, while this last one is 1 0 1. So let me write it again. So 1 0 1, for it I have obtained this one. So this is step number 2. After finding them, we will have step number 3. So let me write the step number 3 by here. Okay, so in step number 3 we have to find the SOP form, okay, from this truth table from the truth table. Okay, so from this truth table we can very easily see that the SOP form what we will have would be, this is X and it will be ABC, okay, plus A B complement C complement plus A B complement C. Okay, so this is the SOP form for the truth table which we have here, and this is this one, and the truth table we have here is this one. So after it, what do we have to do? This will be the final step and implementation or the logic circuit for the SOP. Okay, so this is the SOP expression, and for it I have to find out the logic circuit. So let me first of all write the inputs which we have. So here we have 3 inputs which are A, B, C. So this is first, this is second, this is third. Okay, so the first thing here is this ABC. So let me first write the ABC here. So for this we will have a first AND circuit, 3 input AND circuit, and this will be here. Okay, so this is the first AND circuit. Okay, so the output of it will be what? This would be ABC. For the second one, what I will have, this will be AB prime C prime. Okay, so the second circuit here we will have, so the 3 here, and the 2 inputs here are, this is the first complemented term here, sorry, this will be here, the first one will be here, and the third one here will be here. What? This is the C complement. So at the output of it we will get A B complement C complement, while the last one here is A B complement C. So here let me draw the last here. So let me write the 3 inputs. So that is what? That is A B complement C. So using A here, C here, okay, and B complement here. So from it I will get what? That would be A B complement C. Okay, so we have these 3 inputs which are now added together, and for adding them I will use a 3 input OR circuit. So this is the OR circuit. Okay, and here this is what? This is X, which has been giving me this answer. Okay, so this is what? This is a logic circuit which we have obtained from our expression, which is X, and this is what we had to find out. So here what we have used, this is the first AND circuit, this is a second AND circuit, this is the third AND circuit, we have here the NOT gates and the final OR gate here as well. Okay, so I think these steps are now cleared in your mind, that what steps we would have to follow if a certain output has been given to us, certain input has been provided to us, and we have to find out the logic circuit out of those inputs and output waveform. So I think it's enough for today, and I will see you with some more interesting questions in our upcoming video. Take care of yourself. Welcome back, guys. So I hope all of you will be fine. This is again section 5.5, and we were discussing the pulse waveform operations. So this is question 31, and here we have to repeat problem 30 for the waveform in figure 5.62. okay, so what was basically the problem 30? In 30 we were given this output waveform, which is again here. We can see that this is the same waveform which is here, and we have some inputs which are applied here. We have obtained this output x, and on the basis of this x we will have to see that what will be the logic circuit, okay, which has been giving me this output for these inputs. okay, so for it I previously used a very important concept, and that is the sum of products rule, okay, or SOPs. So what do we have to find out here in sum of product expression? We have to find out in the truth table what entries. The entry is the output for A, which is 1. okay, so therefore we have to identify the same inputs here for which the output is 1, and we can very easily see that this is the only instance at which the output is 1, because this is a level 1. For this we have to find out the inputs. okay, so what are the inputs here? This is 1, this is 0, this is 0, and this is what? This is A, B, C, and for it the output is x, and for it we can see that we have here 1, 0, 0, and for it the output is 1. okay, converting it to the SOP expression, what I will get here? I will get A, B complement, C complement, and that is what? That is the expression or the Boolean expression for the x. okay, so after finding it we have to find out what? We have to find out the logic circuit. okay, so logic circuit here will be what? So let me apply it. So applying it, if we have 3 inputs A, B, C, so this is the first, this is second, this is third. The second is complemented, this is here, the third is also complemented, this is B complement, this is C complement, here we have A, and these 3 are applied to the AND circuit or the 3 input AND circuit. So here we will have this output, and here we can see that this is A, B complement, C complement, and this is x. okay, so very easily we have found out the output, which is x, and by following the procedures we can see that we have found out these things. okay, so what is basically the procedure what we have found out? So initially you have to see the waveforms and see that at which point we have got output equal to 1. okay, on the basis of it we have to find out the sum of the products from the word, from the truth table, and we can see that this is a truth table which has been mentioned here, and on the basis of the truth table we can see that we have found out the logic expression, and from the logical expression we have found out the logical circuit which has been mentioned here. okay, so this is what? This is x here. So I think all the steps are now covered, and you have understood all the underlying concepts, steps which I have followed here. So I think it's enough for today, and I will see you with some more interesting questions in our upcoming video. Thank you so much.